हाँ सही है। हेलो। हाँ, देखे देखे। हेलो हेलो। हूँ। चल तो रहा है। नहीं वहां देखना ऑनलाइन चल रहा है। हेलो। हेलो। नहीं अभी नहीं आ रहा वो। हेलो हेलो। अब नहीं। डबल लेगा इसको चेक करना है ना। हेलो। हेलो। हेलो हेलो। हेलो हेलो।
आप करिए हम स्टार्ट करते हैं. Good morning, everyone present. It gives me immense pleasure to extend a warm welcome to all participants to the day 2 of expert lecture session organized under the GIAN course entitled Modeling and Management of Inverter-Based Resources Integrated Electric Grid. We now begin with lecture 1 of today's session. We are honored to have with a distinguished speaker, Professor Sukumar Kamalasadan sir, who will be delivering an insightful lecture on optimal power flow modeling of electric grid for electric transmission and distribution system. Professor Kamalasadan is a renowned expert in the field of power systems and electric grid modeling, and we are privileged to have him share his deep knowledge and valuable perspectives with us. So without further delay, I now invite Professor Sukumar Kamalasadan sir to begin the lecture. Sir, please.
Thank you. Good morning. We have going to have some fun, a wonderful time with the new rather a topic that is a topic that is evolved from yesterday's lecture. Yesterday we talked about power system modeling, right? Device level modeling of electric power grid, and then we talked about power flow, right? Remember power flow. Power flow models are used to study the electric grid power flowing from point A to point B by calculating the voltages at different points on the electric grid and then finding out how much power will flow from point A to point B. And then these power flow models that we studied yesterday, we studied the power flow models for electric transmission system and then electric distribution system. So these are the things which we studied yesterday. So power flow is basically used to find out if you are given a load on an electric grid, what will be the power transfer flowing through each line or each branch of electric grid, power network, and how much will be the power at each point, power meaning active power mainly, also reactive power, and how much will be the voltage at each point. This is what we call it as a power flow. So there are techniques or method that we use using mathematical models to study the power flow, right? So what we did yesterday was giving you an idea about how these models can be developed for studying power flow. What we're going to do today is extending that knowledge to do something what we call as optimal power flow. Okay, so first we will need to understand what's the difference between a power flow and the optimal power. So optimal power flow is mainly used to obviously manage power flowing from point A to point B, considering the cost. Okay, what do you mean by cost? Cost doesn't necessarily mean money. Cost can be some value. For example, improving voltage on an electric grid throughout as a voltage profile can be considered as a cost. Improving stability margins of electric grid to improve, to make sure that system is more stable can be considered as a cost. So anything that actually gives value to electric grid management can be considered as cost. So this is done through a mathematical method called optimization. Okay, so what we're going to do today is to talk about how the optimal power flows are formulated and how do you compare that with the power flow, how that power flow becomes an optimal power flow, what is the value of this optimal power flow, and what are the techniques we use to perform optimal power flow. It's a basic theme of today's topic. So what we will learn at the end of the day today, hopefully, we know how to do the power flowing from point A to point B. What are the variables, voltages, angular voltages, active power, reactive power, which we studied yesterday. Today, by end of the day, today you will also learn how to make sure this power flowing from point A to point B is considering cost, economical. Excellent, in the simple sense. All right, so what we do is we will just jump on to some basics. Now, if you look at the IBR integration on optimal power flow, again we keep on talking about IBR integration because that is the so this optimal power flow is currently performed on the electric grid. Okay, and there are electric grids, I think probably in India too. I'm pretty sure there will be, but there are electric grid in the US which runs on optimal power flow in operation. Meaning every 10 minutes or every 10 seconds or every 15 minutes, this optimal power flow is run to optimally manage the electric grid. So there are optimal power flow which has been implemented on the electric grid currently. Now, what is an optimal power flow implementation? How that needs to be expanded? How that affects the IBR integration is the topic of interest for our course, GIAN course. So we will have two tasks. We'll have to first understand the optimal power flow methods and techniques, how it's been implemented. Then we also need to understand what happens if IBR comes into place. How do we really need to enhance the optimal power flow? How do we include IBR in the mix? What are the challenges associated with that? Those kind of things. So we'll try to touch upon, you cannot touch upon all the different aspects of it, but we'll give you some flavor on, few things that how we do that. So if you are going to look at IBR, you will be seeing mainly the effect of IBR on the optimal power flow management, including optimizing with respect to some criteria, which is called resiliency and reliability of electric grid, can improve some of the biggest, disasters that can happen or that has happened in the past, including IBR, with IBR in the mix, such as natural disasters, emergence of low tide, proliferation of measurement and control devices, high penetration of DVR. So these are something that actually gives more value to this optimal power flow topic, which has been done in the past because of the challenges of the electric grid that is coming in future. So, efficient load flow method that can solve in a power grid with DER computationally efficient. Can we improve that computational efficiency? The time dependent effects on those dynamic changes. These are the things that we actually talked about yesterday. So if you are going to look at what is changing, we already talked about changing parts are on the electric grid. Our first change is on power distribution system, and that power distribution system was not having a lot of generating sources on the power distribution system. Remember that when we did a distribution power flow, what we did, how many sources we had? If you did a forward backward sweep of distribution power flow, how many sources we had? How many sources we had? one source and then, so that is actually the existing power distribution system. So what is going to happen if you have a lot of photovoltaics connected to it? There will be multiple sources. Okay, such distribution system, power distribution system with multiple sources is now going to be talked as active based power distributions. What do you mean by active? Meaning there are generating sources connected to it. And we also talked about a word called prosumer. Remember what is a prosumer? It's a consumer and a producer, right? Both together, which means generating power as well as. So then the power distribution system will be active. So for example, DER, PV installation, EVs, all those things which is on the power distribution network, make that as an active power distribution system, right? And then you also have devices which are active coming at the last point of the power distribution network. So this last point on the network, like as if you have homes and then connected PVs on that, that is generally called as grid edge. Okay, so you will use this, you will see these terms coming in your life. So I wanted to also touch base with some of the jargons and what is coming in here and why we want. What do you mean by grid edge? Edge of the grid, basically. So these grid edge challenges are also plenty. What are the challenge? One challenge associated with the grid edge, which we talked about it yesterday. We didn't say it's edge, but we talked about one of the challenge with respect to power distribution system. Voltage start going down from the substation to the what happens to the voltage at the edge? Last point, the lowest, right? So this is a known challenge. So if you have a photovoltaic on the rooftop and you are producing power, what happens to the voltage on that point? Voltage will go up because you're pushing power to it. So voltage start increasing. So is that photovoltaic coming on the rooftop at the edge of the electric grid is a blessing? Yeah, it could be a blessing if a voltage. However, what happens if this photovoltaic is producing and consuming? I mean, producing high and producing low, producing high and low. What happens to that? It will become very problematic with respect to the voltage. So grid edge management is also critical. So now we know with this background what is optimal power flow. Optimal power flow is actually will be able to do with the DER multiple things. First, it can save money. It can save electric grid from disaster, which is it will save lives, or it can obviously integrate more renewables into the electric grid. Okay. So this is how the optimal power flow generally can work. So what will be the output of an optimal power flow? What will be the output of a power flow or optimal power flow? Output of this optimal power flow and power flow, what you run the power flow, will be a bunch of set points or reference points that is going onto the devices in the field. Okay, and what does that device do? The devices will be able to generate power based on that set points. So for example, let's assume that you have a PV farm sitting there with battery. You can send a set point to the PV farm and battery and say that, hey, economically or value wise, you should generate 3.3 megawatt. So then there will be a control system that is working on that PV farm to generate 3.3 megawatt. So this reference points, which is coming out from the optimal power flow, can be used to set a given reference to devices, for example, capacitor, and faster changes to devices, for example, lobes, to devices like example battery, and devices such as electric vehicles or photovoltaics. And at the same time, you can also send the signal to the devices like these. What are these devices? We talked about it yesterday. What is this? Huh? What is the symbol? Huh? Transformer. Okay. And what is the line that arrow means? Huh? Yeah, variable transformer or tapped transformer. So you have a tap on the transformer, and we talked about tapped transformer, right? So these tapped transformers can be voltage regulator or the transformer at the side. So now what we are doing is we can send set point to these devices and have the device manage using controllers to take care of the set point. So these devices which are already there on the electric grid, which is controllable, are generally called legacy devices or legacy electric grid, okay, which is already there. These are the ones which is going to be new, or what we generally call as smart devices or newer devices added to the electric grid. So this operation and control happens based on this whole loop, sending set points, feeding the set points back, and then doing optimization based on that. Are you following? Okay. So, the goal of this optimal power flow is basically to generate set points to these devices and that coordinate that set points. So what are the learning objectives? The learning fundamentals of power flow and optimal power flow, learning how to cast distribution system applications and optimization problem, learning how to model OPF problems, and we will also do maybe one hands-on tutorial or test after this lecture today, combining two problem that we said we will solve yesterday, which is on power flow, and one maybe a code-based problem in MATLAB to solve optimal power flow. Okay. So how do you cast an optimal power flow problem? There is a term that I use some terms which is coming from the methods in optimal power flow. One term is cast. Casting means formulating and developing. Okay, so cast an optimal power flow problem means you are formulating an optimal power flow problem. So optimal power flow problem is based on a framework of optimization. Okay? How many of you heard of optimization? The word optimization. How many of you heard of a mathematical model of an optimization or seen a mathematical model of an optimization? 2, 3. Okay. All right. So I need to discuss a mathematical model of an optimization. So what is an optimization problem? Do you know? It's the difference between an optimization and control.
Depending on the object, I think they are either minimizing or maximizing. Like if it is profit function, we need to maximize it. If it is a cost function, we have to minimize.
Very good. Excellent. That is an optimization. Minimizing or maximizing. So why do you want to minimize something? Okay. I know I have to reach here. And I'm here. I can go directly here. Suppose I'm going here, and that's a minimizing problem. I can go here all the way here, not go there. That's minimizing, right? Why do I need to minimize? Why cannot I go directly to the problem? So in other words, I'll give you a set point 3 and I want to go to 3. I can go to 3 using a controller, right? By an optimizer, I will not go to 3, I'll go to some other point, right? Why cannot I go to 3? Why do I need to go only to minimize? Why do I need to minimize a problem? The reason for minimizing a problem is that I cannot get exact solution. That is why I'm minimizing a problem. Now the next question, why do I am not getting an exact solution? So the reason for not getting an exact solution is that there will be multiple variables or multiple constraints or multiple decisions that I have to make to reach at that point. All those decisions may or may not be contradictory. So if it is completely contradictory, I will not be able to go there at all. If it is better, I may be able to halfway go through that point. So for example, I have a point that I need to go, but there is no road there. It's hard to go there. If it is possible for me to get rid of all the, if it is forest area, get rid of all the stuff, I may reach there. But if it's not possible, what will I do? I'll not go there. I'll stop somewhere in between. So the challenge on optimization problem or whatever, whenever I use an optimization problem, you will have to find out there is a many variables that you are contradicting to reach at that solution. If there is no contradiction, obviously you can do that with help of control or other device. You understand the problem, right? So optimization is only used on those conditions. You cannot use an or you don't need to use an optimization. So you have to understand the need. You cannot use an optimization problem for solving something that can be solvable, that can be castable or formulate, able to formulate. Okay? So this is what an optimization means. Now, how do you do an optimization mathematically? Develop an optimization problem. You develop an optimization problem based on a function that you think will let you go to your final destination point. Okay, that function is generally called objective of what you want to achieve. That objective function is any function that is dependent upon two variables. One is the u. Okay, in control theory, this u is generally called controller output or the input to the plant. Okay, that is generally what we call it as u. Controller out or input to the plant. In the optimization world, this u is generally called decision variable. Okay, making a decision. Same thing, but called as a decision variable. So it depends on the decision variable u, and it also depends on x. What is x? You understand this model of state space, right? Have you done one course in control theory? Anybody has done a course in signals and systems? Signals, systems, okay. Control theory. You understand state space? Have you heard of state space model? What's the state space model with respect to a state variable x and a control input u? How do you represent a state space model? Have you heard of this equation? X dot is equal to ax plus bu. Okay, so the input u goes into the plant, and the plant output is basically the state variables. And so similarly, in here, the state variables are represented as x. Okay, in the x dot equal to ax plus bu, what is u? Input variable, right? What is x? State variable, and the output is represented as y. Easy. So y equal to bx plus cx plus du, that kind of a form which you have. Now in the optimization world, state variables x and decision variable is represented as u, and the function that we are going to minimize or maximize is represented as a function of state and the input. Okay. Now many times when you do optimization, you want to go to one specific place or location. You will have a path that you can go through. Okay? This path, there are several paths I can go through to that point. The combination of these paths in a space, we call it search space or a state space. In the state space variable, we call it state space, called a search space for the area. So that area you need to be defined. If you don't define that area, what will happen? Well, you may be able to transfer from any place. Okay, so the definition of that area is important. Okay. And that definition of area is the first thing that you need to go look into. But second thing that you need to look into is that, is there any problem for me to go from point A to point B? Any challenge? Suppose this path is not possible to traverse or go through. Okay, I'll have to avoid that path, right? So that is what in general called as constraint or conditions. Okay, so any optimization problem, if you have a space, you also have some constraint. Okay, if you have a space, how do you make sure that I'm not going everywhere? I'm going confined to this. That is bounded by these constraints. So that's called the boundary. So you need to have a boundary, you need to have a constraints in that, along with that boundary. And that general process is what we call it as constraint-based optimization or constrained optimization. So any problem that is mathematical can be just optimization. But that problem, suppose you cast it into a physical device or a physical power grid, that optimization problem will become constrained optimization. Okay, so every time you will have an objective functions and you have some constraints. Mathematically, these constraints are divided into two parts. One part are the constraints that can be equated. Okay, such constraints are called equality constraints, which can be equated. Some of the constraints you cannot equate. Some of the constraints you can say, oh, you don't have to go higher. It can be same that number or lower. Such constraints are called inequality constraints. So optimization problem has three main parts. One, an objective function. Second, constraint divided into two types, equality constraint and inequality constraint. So can you tell me an example of equality constraint with respect to power flow? We did study power flow yesterday. What are the main two equations in power flow? Power balance equation. So what is a power balance equation? Is that equality? That is equality. So power balance equation can be considered as an equality constraint. How do you write a power balance equation in the form of an equality constraint? So you can say that power generated is equal to power consumed by the load. Power consumed by the load is a great thing if it is the same, but you also have losses. So you say power consumed by the load plus losses. How do you cast that same problem with the PV forms? Is equal to the load power and the loss power. So that same thing which you can. What happens if this PV form power is not a number? It's going up and down. So the PV power can be plus or PV can be minus, right? I mean, if it is, let's assume that it is a net load. You remember the net load we talked. What is a net load? PV plus load. If the load is higher than the PV, it is positive. If the PV is higher than the load, it is negative, depending upon the sign. Sign convention, positive means absorption and negative means, you're pushing. So this can be positive or negative. So what will you do? Well, then you may have to cast it into two equality constraints or one inequality constraint divided into two parts. You may have to cast like that. So this is what our engineers do. We don't do anything related to a lot of mathematics. We borrow mathematics from, like I said yesterday, from different places. But we smartly try to cast or form the problem so that we can solve the problem to get a physical outcome. So that's basically the idea. So are you comfortable with this now? Okay. So we have objective function. We have constraints divided into equality constraint and inequality constraint. So any questions? Make sense so far? Okay. So what is that optimal power operation objective? The optimal point of operation satisfies the network physical constraint and the fundamental rules of the power flow. So now we wanted to go with the optimization problem casting onto power flow. So if the optimization problem, when you cast, I use the word cast all the time. You know what that means, right? When you optimization problem coming to power flow, it is generally called optimal power flow. Okay. So what are the criteria that needs to be satisfied if the optimization has to go into the power flow? Criteria that needs to be satisfied, the optimal point of operation should satisfy the network physical constraints, right? What is a network physical constraint? Can you tell me one network physical constraint? What's a network? Lines. Let's connect. That's network. What is a constraint of a network on a line? Any constraints? No constraints. If you push the power to that network, the network should be able to take that power. If the current is very high, what happens to that network? The network will not be able to. So you have a limit at which the power can be pushed through the network. That network power that can be pushed to the network limit is a constraint. It's a higher upper bound limit for the mathematical problem. That constraint is generally called thermal constraints, which means with the help that power that is going through the network should not go as a heat. So that's basically what we consider thermal constraint. So is that the only constraint on the network? May not be the only constraint. There could be constraints with respect to voltages on a point which is on the network. So that voltage constraint needs to be honored. So if you want to look at optimization problem mathematically, and if you want to convert that into optimal power flow, you have to take care of physical constraints on the mathematical optimization problem. That is where our brain comes, and that is what ChatGPT cannot do or any other thing cannot do, like we were discussing yesterday. That's the place you will need to think while you are working on a problem. So the goal for an engineer should be, I believe, is to make sure these mathematical methods that you are trying to work on has some physical sense and can be applied onto the physical sense. Whether it is a computer science or whether it is any other place, you must think that as a physical sense. That's basically the objective of the smart grid. Many times I have seen people working on optimization problem because that is seen to be very interesting. So for example, there are variable optimization methods utilizing soft computing architecture. For one of the soft computing methods that you can see for, can you name a soft computing method that can be applied for optimization? There are things like swarm optimization, particle swarm optimization. These are variable optimization. Those variable optimization do not have any physical condition. You do just number in, number out, and that is what you need to talk about. So if you wanted to pass that into the operation of the power grid, should make sure it's take care of the physical constraints in the power, and the objective to determine the state control variable to minimize the total condition for the electric. All right. That being said, we'll talk about some of the real physical things. Objective function for now we will talk about optimal power flow. Okay. So there will be a phrase or a short name that comes all the time from now on called OPF. OPF means optimal power flow. Optimal power flow, is this optimization? Yes. Is it power flow? Yes. Is it a combination of optimization power flow? Yes. So you got to remember, power flow comes from physical side, which is like a real system. Optimization from mathematical side, we are kind of merging them together into one. So optimal power flow objective function, OPF objective function, can be loss minimization. One of the objective function that is done in the electric distribution grid on power flow is to minimize the losses. Okay. So what do you mean by minimizing the losses? Everybody understand minimizing the losses? Why there is a value in minimizing the losses? What is the value in minimizing the losses? Huh? Yeah, it is cost optimized. What is the value in minimizing the losses? The losses goes down on electric grid, what happens? Your energy bill should go down because ideally should go down, and the electric utility will be getting power generated in a less power generated because losses go down. If so, losses, I don't know what's the number here, 8%, 10%, something like that. If you go to 5%, 4.5%, 4%, these are the good number which you talk about with respect to the losses. So, in some countries, losses goes up to 10%, 15%, 20%, including, if you include the theft along with the losses, then it's going to be a very high number. But I think we are, in India, the theft factor is very less now, I guess, but so that's what I heard. It's improving with respect to some smart technologies, and the loss is hovering around 8 to 10% or something like that. Reducing the losses can be one of the objectives. What is another objective that you can call that as? Conserving voltage. Have you heard of conserving voltage and reducing the voltage? This is something that is done in power distribution system network. What do you mean by conserving voltage reduction? Which means that the voltage that is being throughout on the optimal on the electric distribution system is conserved. Okay, what do you mean by conserving voltage? So the voltage normally on the electric distribution system has to be between a band, which is 0.95 to 1.05. Between 1.95 and 1.05, what will be your best voltage? 1.05 or 0.95? Huh? One is perfect because you like one, but you have a band, you can go from 1.05 to 0.95, right? So where do you operate? You operate on the boundary of 0.95 to get the better bang for the buck, meaning, losses, or you operate at 1.05 to, you have the room. Yes, you have to operate a little lower, and if you operate the voltage lower, that's the best way that you can maintain. So that doesn't mean you cannot hit to 0.95 because there's a chip associated with it. Voltage is generally going to go lower because of the type of the loads connected to it. So you got to lift and at the same time not lift too much, but you have to leave it like that. Is a tough task. Actually, mathematically to solve that problem is also very difficult because that problem is not feasible, we call it. Oh, there is another term which comes in from mathematics in optimization, what we call it as feasibility. Okay, I will tell you 2 minutes story about feasibility, then we will come back. There are two types of feasibility. One generally feasibility means, what do you mean by feasibility? What comes in your mind when somebody says feasible or not feasible?
Whatever we are doing, whether it is possible or not.
Possible. What do you mean by possible?
It can be done or not.
What do you mean by it can be done or not?
Constants are better.
You can actually, there are different level in the feasibility. First level of feasibility, can you implement this or not? Can you, say, oh, is this whole thing what you did, is that feasible or not? Because, okay, you made all these things. Is that going to be in real life? Can you make a box out of it? If you don't make a box, applied engineers will say, oh, it is useless. And that's not. That's feasibility. Is there any other feasibility? Can you develop this or not? It's a feasibility, right? It's a problem, so it's called feasibility, right? So can you develop it? That's what you're talking about, whether possible or not. Get it done is something very vague. Can we get it done in the box or get it done in the math or get it done somewhere, So that is, you will not want to use. So feasibility spans. So feasibility of an optimization problem is exactly the same. Optimization feasibility is whether mathematically you can solve the problem or cast the problem or form the problem. Well, power flow feasibility means, oh, I cast the problem, I solve it. Is that really good? It's all solved, but the voltage is 0.45. And say, it is not feasible. You did solve, the method is there, nothing is breaking, and the software is working, but it's not feasible to implement. So, feasibility of a problem, when we talk about those two different aspects, mathematical feasibility as well as implementation, whether it's feasible or not. So, having said that, I'll talk about minimizing PV curtailment. Have you heard of the word curtailment? Maybe grounding here on math, I'll go a little faster because maybe you can catch. What do you mean by curtail? Reduce? Remove. Cut. Okay. Cut is a very nice word for curtailment. But cut, when do you cut? If somebody is behaving bad, you cut. Okay? In electric grid, whoever is behaving bad and you cut, you call it protection. Basically, protection is not to take care of the bad folks. Protection is to take care of the good things in the electric grid, cutting the bad one out. That is basically the property of protection. So if somebody is behaving bad, you cut. What happens if you are behaving good? Will you cut? Generally, you don't cut. Curtailment means behaving good photovoltaics, you cut. That is curtailing. Okay, what do you mean by that? So let's assume that the photovoltaics are allowed to supply maximum power from the solar farm. Maximum power is the, have you heard of maximum power tracking things there. So maximum power comes from the photovoltaic. Now let's this maximum power comes from the photovoltaic and you are allowed to get it on the electric grid. What happens if this maximum power at some point of time increases in voltage to above 1.05? Normal operating condition. PV is doing good job. PV is not doing anything bad. It's coming with you and it's coming to you. But we know that if that comes to the electric grid is messed up. What will you do now? You cut. Will you cut it to zero? No, you may not cut it to zero. You may cut it to a level that the voltage is balanced. This is curtailment. So curtailment is not when you behave bad, what is a word that you talk when you behave bad and you want to cut it? Instead of curtailment, you call it islanding. This is the word that you use for behaving bad and cutting. So behaving good. So I just wanted to say the difference between curtailing and islanding, and curtailing and cutting. So what do you mean by cutting? Cutting can be good or bad. I mean, you cut, that's basically good. So you curtailing the photovoltaics is actually not good for us. Why? Because we are not able to gather that power. The power is lost. Curtailing the photovoltaic we are doing because we are forced. So now the question is, can you minimize curtailing? Can be done with the help of good optimization if you do. If you minimize curtailing, what happens? That's basically our value. Value is not just money, but it's also sustainability, carbon decarbonization, the 3D that we talked about. All those things comes with the help of value. So that's what. So now equality constraint, you have power flow equations, equality device models, state related constraints. We talked about this device modeling. Equality constraints means that you are going to make sure that input is equal to output. Okay. For example, there is in power electronics world, we talk about output power is equal to input. DC is equal to AC, 1-to-1 ratio. There is no nothing except for the switch losses. We try to neglect it and then make it small or something. That is an equality constraint. You can make sure that the DC power is equal to 1-to-1 ratio to the AC power without having to make sure that you cut. There also that's a waveform cut. It is not a real power curtailing. So that is actually can be considered as constraint, which is an equality constraint. You can include it. This will normally come if you are trying to do what we call it as DC power grid. DC power grid in a small sense with power electronic devices not utilizing the higher voltage level is called DC microgrid or some kind of a device where you have a DC network. If you go into the higher devices, it is called high voltage DC grid, which is generally classified as HVDC, those kinds of. So the DC network can be integrated to the AC network with the help of this, with the optimization. It's actually you optimize basically DC side and the AC side, and you can put that equality constraint there, right? So any things can be casted in the form of mathematically in the form of an electric grid design. So that's equality. Inequality constraint, network operational limit, voltage bounds, capacity of DERs. Okay, so now with that being said, now we are going to go a little bit denser. Okay, we are going into some math related aspects, but I will try to relate as much as I can with respect to the physical side. We saw this picture before. Everybody remember this picture? What is this picture? This picture is a one line representation of an electric distribution grid. Very nice. And this point of that electric distribution grid is a source that is connected to bus number I that can be considered as a substation. Remember we did a substation, OLTC, there is a voltage drop, and this drawing which we did, this is exactly the same drawing. After this substation you have a LTC. Everybody know LTC? Remember LTC? We talked about the whole story about LTC. Then you connect it to another bus, and after that you connect it to a bus A where you have a load connected at a capacitor bank. Then you connect it to bus M. There is a DR connected load, and there is a bus KL DR connected and load. All these buses can be considered as trunk of the tree, which is three phase. These buses are considered as laterals. Remember we talked about yesterday laterals, and that can be two phase or single phase or things like that. So this is a very small, nice representation of a electric distribution system. We will try to utilize this for our math problem. We'll try to utilize this for our simulation. When you do MATLAB simulation, we'll just try to study in this whole. So if you are looking at this problem, we use this problem to run power flow. Now we are casting the same thing in the form of optimal power flow. Good. You understand this, you understand this, you understand this. What is this? This is the voltage angle of the voltage. This is basically the voltage magnitude and voltage angle that can be used as a state variable, and the current and current angle that can be used as a branch. Okay. All right. So once we do that, now we start looking at some of the other variables. So one, you can have optimal tap setting for the voltage regulator, tap positions, decision on the status of the tap, DER, real power dispatch from the DER, reactive power dispatch from the DER. So this is basically your considered as decision variables. Remember what is a decision variable? It's a variable that you are going to give as an input to the device. So optimization is done, optimal power flow is solved, you take the output of the optimal power flow, you give that input to the device. That input to the device is basically from the optimization side, we call it decision variable. For the device side, it is a set point. That set point is used by the controller of the device and make sure that I reach the set point. So that's the relationship between optimization and the device level control. So the device level control will take that set point, and the optimization world, we don't say set point, we call decision variable. And then how many decision variable you can generate? It's up to you. Any decision variable. So centrally you can look at the whole grid optimization, and then I can say, oh, 7 different decision variable, and give it to the, how you give? Through a communication network or some channel, you give it to the devices in the field. So some of the decision variable include on-off status of a capacitor bank. You can say, hey, capacitor bank, you need to be turned on at a given point of time. You do this optimization on a time basis, snapshot, okay? And every 10 minutes, every 15 minutes you run, so you get this output and then you give that information. DER, real power dispatch of the DER. Oh, so this real power dispatch of the DER, will there be a curtailment? Yes, there could be a curtailment because we are making sure that the system is optimized. Reactive power dispatch of the, and then you can also see AIJ. What is AIJ? What is A? Tap ratio. Okay, we talked about it. Tap ratio. What does the tap ratio do? It changes the taps. When it changes the taps, what happens to the output of the voltage? Changes also. Good. All right. So now we talk about. So we learned the objective function. We also learned the some of the constraints. Now, some of the decision variable. Now we talk about the constraints. There are 2 types of constraints. One constraint is equality constraint. Examples of equality constraint. Voltage drop equation is an equality constraint. Voltage relationship between a transformer is an equality constraint. Power flowing through the branches is an equality constraint. So every power for every point should be related to voltage times current, is an equality constraint. For this network, you have Sij, Sjk, Skl, and Skm. Power flowing. You also have Vj, Vk, Vj, Vk, Vj, Vi for this, and Vj, Vk for this, Vk, Vl for this, Vk, Vm. So if you make it as a generic mathematical algorithm, you can start from scanning the power network for all the nodes and then writing this equation for all the nodes, which is a pretty interesting deal, but it is less challenging because you have to increase the, remember we want to write this on an electric grid, right? Why you want to do this on electric grid? Models needs to be scalable. Remember we talked about it. Then only you can say that it really works in the real life. So that's one of the things that you can see as a challenge. I talk about some other constraints. One, so power balance equations in the network. You can write the power balance equation in the network like this. Sjk minus the drop is equal to Skl plus Skm plus Slk minus capacitor. So you can actually look at the power flowing, the incoming power should be outgoing power and this capacitor power and the load. Are you following? KCL, current coming in, is equal to current going out. So current coming in is this current, this current, this current, and that current. You don't care about these two because you are only considering KCL on that bus. Or what happens if you consider KCL on this bus? Going in is equal to going out plus going out, right? I'm talking about algebraic. This is negative, then when you put negative, that same thing here, current coming in, going out, going out. So there are 3 different equations that is representing. I'm not going to each one of the variable in the equation. You understand, right? In the form of a power. Good? Are you following? Okay. Now we move on to inequality constraints. Inequality constraint comes in two forms. One form is, we call it double inequality, which is voltage, for example, has to be between minimum and maximum. Okay. This inequality is generally called box constraints. What do you mean by box constraints? You are putting in a box. You are actually not saying that it has to be higher or lower. You are putting them in a bucket and say, hey, stay here. Don't go this way or don't go that way. That's called box constraints. You see box to several of them. Oh, how many boxes are there? Depending upon how many buses are there. You have 5 buses and 5 box constraints. You see, most of the box constraints are based on voltage. Following? If I'm going a little faster, you got to pull me down, okay? If you're not understanding. I think in this section, you're okay. I don't know what. Are you following? Yes? Board? Math? These ones are not box constraint. Mainly you'll see thermal limits. Okay? Rated value of the current on the line should be, the actual value of the current on the line should be less than or equal to the rated value of the current on the line. That's the thermal limit. I'm giving you a scope-based method. You may ask the question, can I include other things? Yeah, you can include anything you want, but you need to know what are each one means so you can add more things later. So this is just as a example-based discussion. Okay, what do we do with BERs, inverters? Remember our topic on GIAN is IBR integration 2. So what do you do with the inverters on optimal power flow? We did inverter on the power flow basically. You talked about what you do on the inverter-based resources. On the power flow, what do you do inverter-based resources on the optimal power flow? Again, we worry only about inverters. You don't worry about inverter-based resources. Instead, you worry about inverters. And you assume that the inverter-based resources behind the inverter is trying to push maximum power as possible. So, what you do is, you try to develop an inverter decision equation based on smart inverter. And what is a smart inverter equation that you can derive? You can say that power from the DER, the power from the DER is set by power point tracking, pushing the power to the electric grid. Reactive power from the DER is changed based on the active power and the capacity of the inverter. If the capacity of the inverter is 7 MVA and the active power which you are pushing through this inverter is only 250 kW, well, you will get free reactive power. Why it is free? We talked about the story of being free. Why it is free? No inductor, no capacitor. It is only the difference between the angle on the voltage and angle of the current, basically. And that's what we consume from the reactive power controllable DER, and decision variable is this set point. So there is a big discussion that happens, I gathered when I was in Bangalore, that in India, which inverters needs to be smart and which inverter should not be smart, and how do you control the reactive power from the inverter. I mean, there is some discussions going on. So you could use this optimization method to set how much reactive power should come from the inverter at a given point in a power grid. And that's sacrificing the real power. That is a trade-off. So what you have to find out to see. So for example, in some places you need to improve the voltage, and you are doing in a maximum power point tracking, like you said. You have a curtailment problem, you have to cut it, or if you are not cutting it, you have to improve the voltage so that you can push the power through. So you may try to say, hey, I got this P down, then I make Q up, and where is my good number for P and Q such that I can get the maximum P at the same time, improve the voltage as the same. That's something. And once you do that, obviously, and now there is something called oversizing the inverter. So what they do is that 250. So what we did in a field in US, we had a battery with 250 kW with 750 kWh, 3-hour duration battery, 250 kW. You put a 1 MVA inverter. 750 kWh is a maximum thing, so 1 MVA. So you oversize the inverter to, so you get extra 250 square root of whatever the algebraic addition, but you get a roughly 30% of the reactive power extra from the inverter, which is sitting at that point. and then you can manage that voltage at that point. So all the PV curtailment that the utility in the US were doing, they stopped because of this. Just inverter sitting there, they could push all the, because you have a reactive power buffer. So nobody said that the inverter has to be exactly the same as the photovoltaics. Of course, money wise, we want to make it safe, but you, and it's economy of scale, right? If you have a box sitting there and if you scale it up a little bit, you're not losing a lot of money by scaling from 750 to 1 megawatt, rather than putting another 250 box there and then installation and stuff like that. So all these things can be kind of managed if you think through physically and then understand the physical science, right? So how to balance it. Okay, good, all good. Coming back finally to objective function. Objective function, network loss minimization, minimizing cost for the minimum cost minimization for the DERs, optimal sizing and placement of DER, which is, like I said, not a lot of value, but you can still try do it and see what is the best place. Maximum voltage stability margin. Let's see an example with loss minimization. So how do you represent an objective function for a loss minimization problem? Maximum voltage stability margin. So there is a very interesting question. So optimal placement is an optimization problem. And what optimal placement does is, optimal placement will give you what is the best place to locate a device in an electric grid, considering the voltage and considering what you want to do with the device, like maximum power. For example, DER, your best location will be that location where your voltage is very strong, not changing a lot. So you can get maximum power from the DER. So that is basically the optimal location problem. Optimal placement and optimal location problem is not very realistic, because if you want to get the PV farm located, and mathematically it says that it has to be on the top of a building, and if it is a large PV farm on top of a building, you cannot just do that. Or let's assume that government decided that I'm going to have a PV farm somewhere in Gujarat and some other place, and that is not an optimal location. You still have to do it because it's decided by policymakers and decided by government. So optimal placement and optimal location problem doesn't have it's very loose as with respect to what you can do in real life, because it's not possible to do these things in real life. But that problem has a validity. Now, how do you make sure that it is possible to do it in real life and also problem has a validity? I feel this is what we can do. You find out what are the optimal places that it can work. So you know these are the best places that it can work. Now you look at what the policymaker or government wants. So this is a place. Now you find out to see what is the margin for the stability or reliability of the system if you, instead of placing here, if you place here. Then you find out measures to overcome that and tell back to the government that, well, if you want to place here, well, it's fine, I'm good, but it cost you 200,000, whatever, So that cost you can get it from this kind of methods that we work on. Otherwise, you don't have so the government may come back, yeah, you said that is better than this. How much better? You cannot quantify. You just say, okay, something better, so nobody will really appreciate that. So for that purpose, you still can do the optimization problem. Not very probably realistic, but if anybody is trying to do a optimal placement problem, this is what you should be talking about in that paper or in that publication. Otherwise, optimal placement, whether it is a PV or any other thing. So you understood that context, right? So that's basically what we call that as this. So this is kind of related. You can actually try to find out what is a stability margin. We call it stability margin. Sometimes you think it's very mathematical. Really, it's not that mathematical. If you think about just the stability, you can find out the differences in that. Good. So now let's look at a little bit going down. Okay, so we talked about the story. We are now going into the nuts and bolts. Let's see, how do you really do it? For one example, let's see how this has been done. So now we are going to look at a problem, one specific problem of objective function minimization for loss. Okay. So what is the problem? The problem is to reduce the loss on these lines. Okay. How do you reduce the loss on this? What is the loss on a line? Loss on a line is considered active power loss. Oh, by the way, all this power market is, or electricity market is generally called capacity market, which means you only get money for real power. You don't have any, there is no market for reactive power. Even though reactive power is the one which maintains the real power, nobody care about reactive power. So real power flowing through the line is basically what you want to reduce losses of that, right? So real power can be represented as a real part of this equation as a P loss. Okay. So what is the real part of the I square Z. Real part of I square Z is I square R. I square R is considered as now total real power loss. Or you say all these parts you add together, you get the real power loss. Real power loss is ZJK, real JK, KL, and KL. Why you don't do a real power loss here? Why you don't do any calculate? Oh, in this one there's only 3 terms. You have 1, 2, 3, 4 branches. Only 3 terms. Why you don't have the first branch? There is no line connected. What is connected there? Transformer. It's a transformer connector on that branch, not line connect. So transformer, we don't look at the losses because transformer is considered as a very high, even the distribution transformer can be low with respect to efficiency. I think 85%, 89% is distribution transformer. Sometimes can be higher power transformer is 99%. You don't find the losses inside or reduce the losses inside the transformer, which is not possible, but you can reduce the losses through the line. That's the difference between computer science and power. I saw your face, you're like, oh, okay, that's so we need you, or you need us. Solve. Correct. There is no, exactly. There is nothing there connected. That's a transformer connected. And why we call that still I and J? Because you need to have a voltage on the road side of the transformer and on the source side of the transformer. So you take that and then you call it right. There's no line connected, so you don't really worry about it. So you can actually define specific level objectives such as loss minimization, minimum PV curtailment. So this is how you cast for the objective function for a specific problem. For the voltage, you do this, and the constraints, inequality, and the power balance constraint, right? So all these equations you write. So we'll try to write these equations in MATLAB or in some script, and then you'll be able to solve, and then you'll see how that goes. So what are the putting it all together? This is slide is self-explanatory. You'll understand all the boxes here. You understand this, right? You understand this, right? You understand the power balance, right? You understand the reactive power, you understand the voltage. And this is what we call it as variable definition. And if we did not do this, this is minimizing the total power. So what we did, we talked about optimal power flow. We talked about how to do an optimal power flow. What are the difference between power flow and optimal power flow? We talked about the pieces of optimal power flow. We talked about how the optimal power flow problem can be casted, and we actually put one specific example of optimal power flow problem for power distribution network, considering minimizing the losses. Can you do the same thing for power transmission network? Yes, you could do the same thing for power. Okay, now we will just expand our knowledge a little bit. Oh, so what is going to change if you want to do optimal power flow for different objectives, only thing what is going to change is the objective function. The constraint remains the same. Oh, for a specific network. If you change the network to another network, if you change the network to different DER, it's different. So now you can actually do this for any objective function. Okay. So let's look at how the math or equations transpires into other objective function. If you are doing loss minimization, this is what we did. You understand this, right? If you are doing conservation voltage reduction, you are looking at the real part of the reactive power in that network and try to reduce that for the substation bus, considering the substation bus. So you are actually looking at how much power that is coming out from the substation bus. To reduce that power from the substation bus, what will be the voltages on the network? Okay? Because at the end of the day, you want to reduce the power coming from the transmission network to the electric distribution feeder. If you reduce that power, you will get the cost. So to operate an electric distribution feeder, what will be the power on substation bus is what you are trying to find out. After you do that, you will get voltages for the required voltages for the LTC on the source side. So you can tap and you can make sure all the voltages on this can be. Minimizing PV curtailment. What will you do? You minimize the maximum power from the PV, which is maximum power point tracking, and the current power. So if everything is perfect, this minimal value will be 0, which means the power from the PV farm will be the same as the maximum power. PDG is the power coming from the PV farm. So let's assume power coming from the PV farm is 30. Maximum power you can get is 30. So 30 minus 30 is 0. That's the minimum, that's the best which you can get. Power from the PV farm is 25. Maximum you can get is 30. That's 5. You want to minimize the 5. I mean, you want to make it that go down to 0. That's basically your objective function. The last is voltage. These three problems are possible. This problem is mathematically challenging. And what is that? We call it voltage deviation minimization. Voltage deviation minimization is a set point of the voltage with respect to the actual voltages on the field. That problem is not, it's difficult. What else we have? Oh, another important problem of this decision variable. This decision variable is a set point that goes to the controller. Okay. There are actually 3 types of controllers. I don't know whether you know these or not. One controller is operating continuously with respect to the set point. Here we call it continuous operation of the output. It can be done in discrete form or in continuous form, but it's continuous operation output. Second type of a controller is called on-off controller, where you get a decision which is binary in nature, or 0 or 1. Third type of controller is changing set points in percentage, 50%, 100%, 30%. Such controllers are generally called as discrete set point controllers. So this is a general form. The discrete set point controllers is also in the control theory world called regulators. So if you wanted to regulate a water in a tank, it's a regulator. What a regulator does, it actually looks at the level and then it goes to that level. Continuous set point controllers are generally called tracking. So for example, machines, you don't do regulation. You track the, whatever, speed or, so okay, it's dynamic, and you see how, so tracking is a big deal, meaning it's not that easy to do the tracking, you have that. And the on-off controller, you say, oh, turn it on or turn it on. So the decision variable that is coming out is generally represented in the form of binary for these 3 devices and smart inverter in some of country. You understand this device? You understand this device too? Right? Voltage regulator. This is called a switch. Switch is actually a small brother of a breaker. Okay. And what is the difference between a switch and the breaker? Breaker is controlled. It's operated by a relay or some other devices. Switch is mostly uncontrolled. It opens and closes depending upon manually or automated, but it is not controlled based on some values or changing. That's basically thing. And the breaker also has another feature, which is most of the breakers will have a way to get rid of the arc, and it's called arc quenching media or whatever you call it. On in the switch, you generally don't have that. It flashes and that will go. So you'll have switches which is a lighter version of a real breaker deployed on the electric distribution system. There are a lot of switches deployed. So you can open and close the switch depending upon a binary variable. So now I will talk about methods of optimization. Okay. So we did, everything is good. How do you solve it? You solve it using mathematical optimization solver that you borrow from mathematicians. Okay? And you don't. So there are different types solvers. Let's assume that you put all these problems that you write in the form of a linear equation. You can use linear solvers to solve linear equations. Such linear solvers that is used to solve linear equations are generally called linear programming solvers. So one way to solve an optimization problem is through linear programming. It's also called LP. Unfortunately, electric grid power problem, when you write a power equation, it is non-linear. Why it is non-linear? Because you have voltage divided, V square divided by R, fundamental thing as far as power is concerned. For a current and voltage is not a problem. So this can only be solved through solvers which are not linear, which are non-linear. Such solvers are called NLP solvers or non-linear programming solvers. So we learned about LP, we learned about NLP. Can you cast this problem as a linear program? Yes, you can cast this problem as linear programming, reducing the non-linear part and call that as a linear. So you can do LP or you can do NLP, right? You can only do LP and NLP if the decision variable that you are coming out is continuous in nature. If the decision variable is binary, for each of those binary state, you have to do the optimization problem separately. So you have to look at each state and then do optimization. Every state is also unknown. What state you want to put is also. So you have to solve this through integer programming to get the binary state and linear or non-linear programming to get the other devices. So it will be mixed integer linear programming or mixed integer non-linear programming. So now you know what this means. So ideally a optimal power flow problem is non-linear in nature. If you have a decision variable which is binary like a capacitor or something, then you must use mixed integer non-linear programming. Unfortunately, this is one of the hardest problem to solve in optimization world. So this is a problem for the So what I'm going to do is I'm going to stop here and then I will need some time to continue on the next lecture. Any questions? 2 minutes. Next lecture is going to be talking about the linear programming, non-linear programming, and the optimal power flow to solve this. It's good? Questions? Any questions? Are you understanding? All right. And I'm going to continue without any but my task for this GIAN course is a little tough here because I am asked to talk about one type of method, solve this optimization problem called convex optimization. So convex modeling is a way to make it computationally faster and at the same time making sure that all the parts of the nonlinearity is included. Okay, so that's basically my goal. I don't know how many of you are aware of linear programming or how many of you are aware of linear programming. Okay, how many of you have solved a problem with the linear programming? I have 3 people with me, so that's good. How many of you are aware of nonlinear programming? How many of you have solved a problem with nonlinear programming? So that's one. How many of you are aware of mixed integer linear programming or nonlinear programming? So you will be my friend. You will be able to work with me and then do that. And then after that, convex. So what I will do, I have to stick to my scope, but at the same time, I have to make sure that you understand. So I'm going to scan through some slides and then give you some best judgment of other 2-3 types of programming. Then I'll go to convex optimization and talk to you about how the convex optimization is done. That's basically part of the. What is the other? I was thinking I will continue. I don't know. Anybody wants to have a break? Because it will recoup again, right? Because then it will be, No, it's fine. I'll go with the flow. It's I like, but looking at the noise and the disturbance factor comes, because that. So let's see. What we can do is we will try to do it in 1 hour, and then we'll entertain questions. Last 10 minutes will be like discussion questions. So, linear programming, by the way, is pretty much understood, and people understand the linear programming. Linear programming is a characteristics, is a well-defined single objective, must be stated. There must be alternate course of action. The objective in each of the constraint must be expressed as a linear mathematical function. Okay. Oh, by the way, when you say linear, non-linear, and all that, what does it mean? It means that the objective function, there are 2 parts in optimization: objective function and constraints. What happens if this objective function is linear, constraints are not linear? You have a challenge because you have to make the constraint linear, right? So people talk about both type. So for example, suppose objective function is quadratic, second order function is quadratic. So you call it objective function quadratic, is called quadratic programming. If the objective function is quadratic and constraint is quadratic, you call QC QP, quadratic constraint, quadratic programming. To define what are the objective functions and constraints and which linear constraint quadratic programming, LCQP, you will call it linear constraint quadratic. For each of those, solution methods are defined by mathematicians and they solve it. So you will see this term coming to you as constraint, and programming is defined for function, objective function. Constraint is C. Programming is nonlinear programming. Nonlinear programming is all dependent on function, and the constraints is actually C. So just to give you the jargon, otherwise you'll see hit with these very, I don't know what's going on. Understand, right? Okay. So we just quickly go through this. This is something which is math, but I'll put this slide here, which is important. What is the assumptions for linear programming? There should be conditions of certainty to exist. That is, a number in the objective function exists with certainty and not subject to change. Okay. There is an objective function. There is a number inside that objective function. That number is there. It's not moving. If it's moving, then you cannot get this. You cannot find it. Linear proportionality, linear additivity, divisibility, non-negativity. These are some mathematical aspects for linear programming. So LP problem in standard form looks like this. Okay, this is objective function. See this objective function here, C times X. It's not X times X. C is basically what you call it as a constant that you are representing multiplied with X, which is mx plus b form. Linear iteration, linear iteration and linear optimization. Linear iteration, regression. No. I'll have to explain a bit. So there is something called so there are three words. Okay, I'm just putting three words. One word is called approximation. Okay? Approximation. You know what approximation. So you have an ax square plus bx plus c, and I say that ax square is not required. Bx plus c I used. This is approximation. Instead of approximation, I do aggregation. Ax square plus bx plus c. And I'm going to say that ax square will give bx plus c and be added together and call it c square x plus m. This is aggregation. Okay. Third one is something called relaxation. I'm going to say ax square plus bx plus c. I cannot solve this. I do ax square as am plus bx plus c. Now m is x square. I know that on the back of my head. I'm not going to say that to the solver. When I trick the solver, am plus bx plus c. Somehow where to find the solution. Now I take this m and I try to find what is x from the m. So I'm not losing anything. I'm relaxing some. I cannot find x. I'm in trouble from m. That's my problem. If I can find x, then I'm a brainer. People will say, oh, I get the exact value of x without losing it. Three different. Regression is a process of optimization. We're not optimizing anything. Regression is a process of, all these things are not optimization. Relaxation, approximation, and aggregation is not optimization. It's a way to reduce the complexity of the problem and how to work with the problem. That's all. Okay? Regression is a process of trying to what? What is regress means? Regression is a process of trying to come up with the best fit on a specific equation and find out what is the best fit on the equation. So you're not approximating, you're not relaxing, you're not aggregating. The closest will be probably you can say aggregation, but you're not really aggregating and you're finding out the best. So that now you understand the difference. So there today. Now convex optimization uses this interesting concept of relaxation. So that is why I'll come to that and then I'll say how to, we call it recasting the problem. Casting. So I use the word casting. Recasting. You can recast multiple times and I'll get something very clean. But inside that, there will be a lot of dirty stuff which I need to unwind, which I'll do it later. That's basically what is called as convex optimization. But, so you understand the difference, right? So, by the way, so this is the LP problem. If xn satisfy all the constraints, then it is a feasible solution. Maximize the objective function is called the optimal solution. Okay, so you see feasibility and optimal value. Can I move a little bit faster because we are working on convex optimization? Is it understood? So then you have for the linear programming, what you generally do is you try to add two new variables on the existing framework and trick the system. These variables are called slack variables and surplus variables. Slack variables is added to A when the A is less than or equal to constraint to convert that into equality. So if something is less than or equal to constraint, then you make it equal by adding this slack variable, right? And why I want to make it equal? Well, then only I can work with linear programming. I cannot work with linear without that. And if you have another way, I'm surplus. So then you do two different methods in mathematics. One method is called graphic approach. It's restricted to two decision variable. The second method is called simplex algorithm. It's used by a matrix operation. Oh, by the way, this is interesting. Cxj is equal to m. What is x? M divided by c. You see? Now Cx is a column vector. C is a matrix. C times X is equal to M, column vector. What is X? C inverse of M. See, that means just by matrix inversion, you can get the solution. That's the method of linear programming. So, here is a graphic approach. Some examples here. Special cases, you can just skip that. And these are solutions, bounded solutions and unbounded solution. In a simplex method, you will make a table and you try to put the variables. These are in the books, by the way. So you can take it from the books and then understand how it's been done. I'm not explaining that. Everybody might have done one part in simplex. You make the steps and then you try to reduce with, oh, these are the variables that you're adding. And by the variables, you try to make the table and reduce the table step by step, and then you can reduce. I just breezed through. It's okay, right? It's math first, you can read. Good? Okay. NLP. This is the forms for nonlinear programming, and this form you already have seen. In the nonlinear programming, these variables are all nonlinear in nature. So you see f of x, g of x, h of x, right? Scalar objective function, n variables of vector, inequality constraint with m vector, m equality constraints. M eq is basically the vector for that. Sufficient condition for a unique solution is f of x must be convex and a feasible region must be convex. Do you know in the math the convex functions and concave functions? How many of you heard of convex functions? I have to move on the screen. I can do this one after. This is a simple representation of a convex function and a convex. So if you have a ball, a closed loop ball, you have a stable point, you go to the ball and then sit there and then you can find the minimum value. And if you're finding this is actually close to this, exactly this point, this is probably your optimal point. Okay. That optimal point, if the, oh, by the way, minimization problem. If the minimum point or minimization problem becomes 0, what does it mean? That's the best scenario. So for example, PV power coming out, cut maximum power minus the actual power is 0, which is the maximum power function. That is basically the best. So your goal is to reach here. Again, why you cannot reach there? Because of constraints and because of the problems challenging, you cannot reach that point. That is why we use optimization with, we call it minimum. Okay. If you are doing in the form the same thing as a control and cast this as an error, and that error becomes 0, that's the control. So that means you have a control taken care of. Controllers are basically one input, one output. What happens? Multiple input, multiple output controls or multi-variable controls is going to be challenging. You cannot just get that. So if you are going to minimize that problem, oh, can you find the maximum and find the inverse of this? So you can take that same function, flip it backward, and then find the maximum point. That's also good. So many times optimization folks, oh, by the way, what I got an optimization problem, results made, decision coming out. How do you know that's good or not? Challenge, right? Because it's a optimization done and it's almost like a wish list. Oh, I have a goal to make it. Yes, if it is a photovoltaic curtailing, I can know it's good or not. I can match with the maximum power. Some objective is not possible. So you know what optimization folks does mathematically? They will invert the problem and find the maximum point. And you find the difference between this. It's called gap or optimal gap. The best point is when there is no gap. They hit with each other, which means optimization is solved properly and there is no gap. No gap doesn't mean that it is it is going to 0. Minimum value, it may be sitting at 3, may be sitting at 4, but no gap, no? Which means, it may be, what I mean by that is, this line may be here. That is also, it's a gap, okay? So, this is how you work with optimization. So, any optimization problem, you can get a feasible solution or a good solution if the curve is like this. If it is like this, it's hard to get the minimum value or a minimum solution or a feasible solution. So, there is a condition in every time you say in optimization world that the objective function has to be in a convex form. Now, what happens if you get an objective function in the concave form? You recast that problem and bring into a convex form and then solve it and then do your things later. So, Gx is all, Fx is convex, Gx is all convex and Hx is linear. Except in some cases, there's no guarantee that local. Oh, by the way, if you have a point, I want to mention this also. This point that you reach in this function is the best point, right? What happened if the optimization solver found this as an optimal solution? And you are here. Yeah, this is optimal. I agree with that. This is also optimal. Yeah, I agree with that. So everything other than this is all optimal. But there is only one point which is the best. And that point is called global optimal. Globally optimal. Okay? So for example, this is a nice curve. What happens if you have something like this? This is also convex. Weird convex. So you have optimal point here, optimal point here, optimal point here, right? So all the other points which are not globally optimal are called local optimal. Okay. So you see something what you see here, local optimal. Okay. So there is no, except in special case, no guarantee that local optimal is global if sufficient conditions are met. So then there is another term in optimization world, people call that sufficient condition. Okay. There are two words, sufficient condition and necessary condition. Okay. Do you know the difference between those two? Necessary conditions are obviously necessary. You must have that condition taken care of. Sufficient condition means at least these conditions are good enough to find a solution for the problem. Other condition, even if it is not there, you still can find a problem. Right? So the local optimal point is global if sufficient conditions are. If sufficient conditions are violated, what happens? Obviously, you would not get the results which are going to be optimal. Yeah, some graphs there to talk about linear programming. Another thing which I wanted to talk about is some two other things comes in math called definite matrix. Have you heard of positive definite? Okay. Negative definite. So positive definite conditions are basically required to develop any problem, even if instability problem, every time you need to have a positive definite condition. So having said that, positive have you heard of semi-definite? Positive semi-definite? Okay. I don't have to explain, right? You understand. One is greater than 0, one is greater than or equal to 0, and there are some sufficient conditions when mathematics they are developed. I'm not going to talk about that. there is something called KKT, Kush-Kentaker conditions, which is developed for working. Now you go to quadratic program. Quadratic programming is represented in this form, okay, which is A transpose X plus 1/2 X transpose BX. You see, this is linear, this part is non-linear. Can you see that? Why that is non-linear? Because X transpose times X, you are actually, square. So you can be solved using LP techniques by reducing this to the LP, and you have some condition that B has to be positive definite, then QP solution is unique. If B is positive semi-definite, optimum value is unique, and there are some requirements. These are classically solved by people, so it is there in the books and things like that. So here is a representation of quadratic programming in using LP. You can solve that using, one way to use a quadratic programming using LP. How do you solve it? So this is actually classically done in economic dispatch. Have you done any course on power system operation and control? Yes. Have you heard of economic dispatch? Economic dispatch, you have a cost function for generator represented in the quadratic form. Okay. What is the way to solve that quadratic form function without using quadratic programming? What you do? You take a derivative of the quadratic function. Take a derivative of the quadratic function, then it will become linear function. And you equate that to 0. Oh, by the way, I think this is probably known to you, but I don't know whether you know it. What is this point? What is the derivative of this function at this point? So you take a derivative of the quadratic function, equate that to 0. This is what we do in economic dispatch for a cost function for a generator. Economic dispatch is not optimal power flow. You can extend that to optimal power flow, but you can compare generator cost function. So that's one way you can do. You will see something is written in that form. And quadratic programming can be used. Another way of writing the quadratic programming is through quadratic programming with respect to time, multiple times. It's called sequential quadratic, programming. Again, I'm not going to go through this. Let's keep the algorithm. So some examples that we did. One of our tests here on comparing sequential quadratic programming with nonlinear programming, finding out the voltage profile on a system and then checking it out, and the transmission network related results. So these are some of the basics of. I will start with convex optimization. Here is an optimization, real optimization problem. This is a network, a real feeder, which is unbalanced, which has 9,500 single phase nodes, 107 switches, 1,275 single phase nodes, 354 single phase PVs, and then DGs and storage. So if you want to really work on a field-like problem, you can see the number of variables and the decision variables and things like that really work on. So that's a very important question. So it can exponentially increase to 350 minutes, 500 minutes, 700 minutes, 800 minutes, that kind of number. So what you do is no optimization problems you can solve without divide and conquer. So you try to divide and conquer. So one of the approach that is used in the field is to using parallel computing. So you run it on GPUs, and parallel computing where all the knowledge on software and other things will come into place. And there are high performance computing infrastructure HPCs used for solving this kind of optimization. One of the fascinating part of this optimization world is that everything is directly related to cost. So there is a direct deliverable sitting there, except for it's investment wise it's there, and then people like it to do. Some of the utilities. So for example, a system operator in the US run the optimal power flow every 10 minutes for 30,000 bucks of electricity. They invest it on the because that's a value. That's a lot of generator using of generator, cost associated with how generator should change with respect to time, what power it should come, especially with renewable, is generally called as resource mix. Resource mix means when the renewable comes in there, there's a dip in generation in nighttime, and then high peak in generation. So this dip and peak, if you have generation dip and peak, somebody has to compensate, sit there and compensate for that. So the gas turbines and other folks are sitting there and trying to, they call it ramping up and ramping down. So this goes up and down, goes up and down all the time. So if you want to find out what is the best resource allocation, one gas, one nuclear, one hydro, one renewable, this is a problem that is a future problem because people don't know. In conventional olden times, you don't care about all this and you put the stuff in. When renewable comes in here, so that affects the optimization world, that affects the electricity market or capacity market. So the problem is complex, but methods to solve this problem, if somebody can do it realistically, utility likes it. But there are a lot of mathematicians and people like us solving it without not real. So like mathematically you can solve something, but they come up with a solution. So there was one paper which you were reviewing. It says there is a solution. Yeah. You can put that, and you put a solid state transformer. Is it head of solid that in one location, and then everything works well. Solid state transformer is technology is not even mature, and you cannot even buy that box. But that's a math world. So there are folks who does both. Just giving you some stories because it's a very interesting, so algorithms that has to be scalable. Otherwise, you cannot do anything. That's the whole thing. So now we will talk about convex optimization. So this is an example of approximation and relaxation. So what are we doing in approximation? We are cutting some things. Okay. So you see right here in the approximation, what we are doing is we are approximating this whole thing and this box. Now let's assume that you don't cut. You put everything in the form of a bucket like this. Okay. You are okay. But if you do that, you will have a lot of space here. You may get to this point as an optimal solution. It's not feasible. You may get into this point as an optimal solution, which is not global. So this is the challenge with respect to approximation. Instead of approximation, if you relax, what are we doing? We are extending the space and to cover everything in a bucket. So you are now, the only challenge is you have to find it here in the green area. If you find it somewhere else, you are gone, right? So this is the difference between approximation and relaxation. Make sense? So there are different category of convex optimal power flow models. Okay, one type of convex optimal power flow model are based on voltages on a bus. Okay, and power injected on a bus. Okay, this is done through solving node voltage analysis, basically. So those node voltage analysis, when you solve it, you will not have any current flowing through the line, but you convert all the current variable in terms of voltage and you solve for voltage. So this is what you do for voltage-based studies. Such models are called BIM, bus injection model. Bus, remember bus injection model. Okay. Another model is, okay, I don't worry about voltage, I only worry about current. So you recast the whole problem in the form of current. When you are looking at a current, you don't look at the bus, you look at the branch, because current is flowing through 2 points as a branch. Okay. Such models are called branch flow model. Okay. So there are 2 types of models in OPF: bus injection models and branch flow models. These injection models are very useful for, we already know the story. Bus injection models are very useful for transmission networks. Branch flow models are very useful for distribution networks. So you can categorize them and put it together. If you do both of them together, it's a different deal. But you can actually use these 2 models. Now there are mainly 2 different forms of matured optimal power flow problems using convex optimization. One method is from mathematics that we borrow is called SOCP. Okay, SOCP is represented for second order cone programming. Okay, so what you do is you write this whole relaxation space in the form of a cone, and if you put it in the form of a cone, it's basically a structure that you can derive linearized forms from that cone. Okay, so cone can be written, equations for the cone can be written nicely in the form of a cone. So it is obviously coming from what you call second order cone programming. The other type of convex optimization runs into a group called SDP, semi-definite programming. Semi-definite programming, you know what a semi-definite means. So basically 2 different types of OPF, and there are methods to relax the problem. Is one of the methods that is used for relaxing the problem is a method developed by McCormick. It's called McCormick relaxation. Okay, so we are going to discuss comparisons between semi-definite program relaxation, second order cone program relaxation, and linear AC problem formulation. So here is our problem. We casted this problem again. Everybody understand these 3 equations? Yes or no? Yes, we have objective function, equality constraint, inequality constraint. So to model in a linear programming, this condition should be f of x should be linear in x and u. G of x is affine function of x and u. What is affine means? Affine means linear. What is linear function of f and u? Affine function of f and u, what is the difference? In the affine function, your conditions can be non-linear, but the functions has to be formed in the casted in the form of linear. Okay? That's the difference between linearity and affine. And f of x should be an affine function. So, for example, power flow constraint corresponding to equality constraint, and they are non-linear in nature, but you can be recasted in the form of a affine thing. So, let's look at the power flow equation. This is the power flow equation. You remember this? This is called, what equation is this? Voltage drop. This is the power balance. This is the apparent power equation. Now let's multiply both the sides by equation by their Hermitian transpose. You know Hermitian matrix? It's a little bit of math here. Let's say there is a matrix called Hermitian matrix. I'll talk about Hermitian matrix later. So if you take a Hermitian matrix and you multiply this Hermitian transpose, what we are doing is you are multiplying this Hermitian transpose. You are multiplying this right here and then this here. So you will can cast this whole thing in the form of this. You agree with that? Can you see this is this Okay, how do you see that? Not a big deal. Can you see this? You cross multiply and you should be able to get it. Right? I'm not doing the math in here, but you can check. So, what are the nonlinear type of parts in the power flow equation? You see this equation when you look at in the back right here. What is a nonlinear part in that equation? You see right here, this is S, Z, Z, S, and Z, L, Z. This L is actually what we are writing here is I, J, I, H is written as L, right? So you see this is the one that is introducing the nonlinearity. Are you following? Right? Any square term that is introduces the nonlinearity. So this term and this term introduces, these two terms are not introducing the nonlinearity as such as the problem is concerned. So what do you do? What is the easy way? Whatever is introducing nonlinearity, cut it out. Okay? If you cut it out, this becomes linear. Yes. Do you have a method to solve it? Yes. What are we losing? What is this? I square times Z, right? What is that? We are ignoring the, from voltage drop, ignoring the effect of power loss term on the voltage drop. Okay? The effect of power flow is still included. Power flow is happening, but power loss term is neglected. From power balance, we are ignoring the power loss term, basically. Okay? What happens if you ignore the power loss term? Will you be able to solve the power flow? Yes, you will also. What happens if the loss is not included? Well, if the loss is not included, you will lose the value of the loss or whatever cost which you wanted to generate the extra power. Okay, so linearized approximated power flow, you can actually write this part equation. I don't know whether you can see this right here is the same as this, right? So you can see that part of that equation and then you can solve for the power represented like this, and you can separate the power into real and imaginary part, two part, linear in state for the power QP and decision variable PD gens, all are linear. See, they're all linear, and you can, if you look at this system, this is called underdetermined system. We are not doing the math in here, and you can solve that math with approximations, and you can actually utilize that and then get the solution. So let us try looking at that for our system. This is our small system, and this is the power balance equation. This is the linear power flow. Oh, by the way, when you solve for a system, you will be looking at the power flow equations and you will be looking at the optimal power flow. So this is a voltage that comes out from the optimal power flow. Voltage that comes from the power flow. You see that the voltage is different. Why the voltage is different? You are reducing the loss term in this. But your shape of the voltage remains the same. You see? So you have to consider that and you can solve it. Okay, good. Now we're going to use this for with the convex optimization technique. I'm going to, essence of time, talk about one specific key aspects on the convex optimization technique. One method of convex optimization is semi-definite programming, SDP, right? So SDP, you can represent this in the form of AX less than or equal to B, and with what you call as trace. Trace is basically a matrix, how to find the trace value for that, okay? So we look at the same problem. You see this here, Z nonlinear, right? Z nonlinear, right? First what we did, we tricked the math for a computer. Instead of I call it L. So this I becomes L. So what did I do? I made that I is I square into a new variable L. So the computer thinks it's linear. It will be fine. So that L I put it here. This becomes right here. This becomes right here. Now you look at the rank of this matrix and find out the rank, whether the rank of the matrix is good. And the rank is 1. And after you see the rank is 1, you drop the rank constraint, make the problem. This rank equal to 1, if you making problem non-convex, you drop the constraint. That is called what we call it as relaxation. Now, once you relax that, you can solve it. So with our same fibers example, this is the power flow equations. This is the rank for each of those buses. And after you find the power flow equation for each of the buses, you write the power balance equation. And we relax the, what are we relaxing? We're projecting the voltage and current variable to a higher dimension and making the rank equal to 1 as a non-convex, you're dropping to achieve the relaxation. If after solving the rank is not equal to 1, the solution is not feasible. If after solving the rank is equal to 1, solution is feasible. So you can actually use that for solving using convex. If you are going to represent this in the form of second order cone programming, you will cast these power equations like this. Okay. This power equation has a very nice feature that is much like a cone. So the cone equation has got a cone definition is coming from a circle at the base. So when you have a circle equation, you know that x square plus y square is equal to m or c. That's a circle form. So this is actually a kind of circle, but you can relax that as a second order quadratic inequality in the form of a cone. So if you look at this is non-convex. You agree with that? Because you have square term, right? It's non-convex. But you put that in the form of this inequality. So if you put this in the inequality, then it will relax in the form of a cone. So that is basically the cone function. Now the solution, so this is like what we have for the cone function. And if you have a cone function solution, you can actually look at this cone function, cone, and you can solve that cone equation with the help of a solution for cone. So there is a classical representation of how to solve a cone function and utilize the cone function to solve. So if you do that, then you will be able to get a feasible output solution. And here is an example with 5 PV located on a part of an electric grid, and you can actually utilize to run the cone programming. So basically, I will stop right here, and maybe we can, after lunch or some, we can do some small examples for test.
Thank you, sir, for that insightful session. I hope all of you enjoy the session.
I know you are.
If you have any queries, please ask.
Yeah.
If you have any queries, please ask.
We are almost done with the time, but anybody has any questions? Of course, no questions, because we can have lunch or it's too hard or whatever. But anything that comes in your mind. This time I pulled my time. I made sure I gave only the essence, one, not the non-essential. I mean, there are, I don't want to say non-essential, there are great mathematics part there, but I try to keep the, right? Is okay, right? That level, I don't want to go to the,
mathematics as well as
yeah. And then, they can work on it, and then, they have to do it separately. But I gave you the real part pieces that is to it.
Thank you, sir. Now we have the tea break outside the seminar hall. Please have a tea. Okay, and all of you request, please assemble at 11:45.
11:50.
Sure.
हाँ, पर से थोड़ा ये तो सही है।
ये अच्छा हो गया।
हाँ
Last yesterday you did a good
Welcome back, everyone. We now begin problem solving session with example to be delivered by delivered by our esteemed foreign lecturer, Professor Sukumar Kamalasadan.
So we have two, ready? Do some fun stuff. We have two part which I'm thinking. One is using, by hand or, calculator or a computer or some. Another one is using, doing on a software, some software. So one thing which is pending from us is to do a power flow example from yesterday. So we will do two. One is a power flow example and one is an optimal power flow example, right? And then after that you can ask any other examples that you want to solve, and then we can do solve. So I'm thinking first we will do the power flow example, right? Is that okay? So you want to try this? Yes. So what you can do is you can actually write the impedance matrix. You want to use your computer, you can. How many of you are proficient in solving something using MATLAB? You're okay, right? Okay. So then what you do is you write it in MATLAB and solve it. You don't have to do it by hand. Okay. How do you write it in MATLAB? Do you know how to write this matrix in MATLAB in a command prompt or something, or you can write it in the form of a script? So I don't know whether, I don't know whether this is, there are several ways of doing the problem solving. So let's give you some. How many of you are not proficient in MATLAB? Not proficient in MATLAB, meaning? Can you, will you be able to partner or join? You are good in MATLAB? No. You are good in MATLAB? He said no. You are good in MATLAB? No. Are you good in MATLAB? No. 5. How many? You just keep saying, that's no problem, okay? How many other are there? Okay. So we may want to probably pair or something, I guess. I mean, need to need to have fun. Otherwise, you will be sitting there and not playing. So just okay. So if you are looking at MATLAB, you get to do in two ways, right? One thing what you can do right in MATLAB is write something in the command window. Do you know how to? What is the command window, right? Command window is this. Right? So you can write, say, this impedance here, you can write in the form of a matrix, right? Impedance 1, impedance 2. That's one way. You can write it in a script, right? Script means in a white space, you can open a white space and write it. Okay? So can you start doing? Everybody comfortable writing, right? Not by hand. You know, hand is a little take. And whoever has finished this first should raise hands. Should not be doing that. Oh, not that. I thought somebody would be doing by now. Fast typers. Good, done. Good. Okay, so they should be able to do it. Oh, so anybody has a question on how to do this in MATLAB? You open a square bracket and then you write the first, IE, complex, then you put a semicolon, then you go to the next, right? Do you find anything interesting in this matrix? Anything interesting? Can you make use of that interesting things to do it faster? It's actually coming from the physical grid property. It's not a made up. You see, Z bars also like Z13 and Z31 are the same, right? Z23 and Z32 are the same. Can you see that? It sounds like a bunch of numbers, but they have a pattern. The pattern is that these are off diagonal elements. These are the same, right? You see, C12 and C21 are the same. C3, C23 will be same with what? C32. You see that? So why it is like that? Because the transfer impedance between two number or two line, the same impedance, and you cannot change that impedance both ways. Whether you look at this way, whether you look at this way, they are the same. So what does it gives you with respect to your working in MATLAB? You can copy paste. I think he also said that he is not comfortable with MATLAB, right? He also said he is not comfortable. So you all the three uncomfortable ones got a computer and then you still not done. I don't want to do the full show and tell. That's the reason I'm forcing them to do it. You're okay, right? And otherwise, what happens is I'll show and tell. I'll give them. They will just click the button, and then because the other way is to give it. If you give it, then it will not do it. Very good. Okay. So since both of them, right? Both of them you're done with both of them. So what you'll get a level of understanding here That's the impedance of the two parts, and the impedance of those two parts has got some symmetry. Symmetrical. The matrix is symmetric. What do you mean by symmetry? Symmetry means the opposite of diagonal elements in image set. And then diagonal elements are the ones which is basically come. I will do something. Can everybody see this? In the back, can you see this? Okay. Who has done the first part on the impedance? You can start on this. So you wrote these two in a script or a command window. Whatever you wrote it, right, on a script or a command window, you can start making a matrix which is V1. And a load. Cross it. Yes. So the elements are complex numbers. First one is impedance of one line. Second one is the second element on the right is the connection between 1 to 2, and the third one is 1 to 3. So this is the impedance of the first line. So this line is actually 3 lines. So it is more like a very good question. So it is more like a so this is I say 1 1 just, and this is a 1 2. This is 1 3. Similar 2 1 2 2 2 2. That's for one segment, meaning bus number 1 to 2, and we call it Z12 or something. Then you have another one like us. That's fine. That's fine. And that is because the unbalance, right? I mean, 3. So if there is no unbalance, interesting part there. I don't know whether many catch that. Yes, if there is no unbalance, this will go away, that will go away. This one then will become. That's what we do on the transmission network. Done? Oh, still almost. So you are making three metrics, right? One is voltage and two loads. Three. You're doing on a script or a command window? Command. In the command prompt you are typing or you are typing on the script. So are you typing the variables here or on a white space? Here. Okay. Just info. Don't do anything. Just so when you do this, don't use the number, but use the equations you have. So for example, you have a voltage that is 2400, 2400, 2400 in a matrix, which is 24, 0, minus 120. So that voltage you might have given a variable V, I don't know, some variable you have V equal to and a square, matrix. So you say V open bracket 1 comma 1, which is the first element. V open bracket 1 comma 2, second element. V open bracket 1 comma 3, third element, right? So you say, and 127.5 J80 is the S12 1 comma 1, something like that, right? What is the load? So if you look at this S, I don't know whether you've written S load 3, I don't know, whatever the variable you said S load. Yeah, so X load 3 open bracket 1 comma 1 is 127.5 plus, and V1 is 2400 right? No, you said V2 and V3 is also the same. Did you say that? On V1, okay. So then you go ahead and say V2 equal to V1. Say like that. V2, V underscore 2, or I don't know, whatever variable. V2 equal to V1. Then equal to is assignment. You know that, right? If equal to is not equal to in MATLAB. When you say equal sign, meaning you are assigning the left, right to the left. So V2 equal to V1 and V3 equal to V1. Right. And after we have done V2 and V3. That's fine. You can write in polar and rectangular. It's up to you. Write it in rectangular. So V2, V3 you already, right? Now you use V3 with type V3 open bracket 1 comma 1. Underscore 1. This is V1. Okay. Yeah, don't use the brackets here, right? Write V1 to underscore 1. Please. Good. Do you know how to know whether this is correct or not? So you highlight this from here to here and click F9. Yeah, you click F9. Yeah, F9 will be different. So that's some error in that. So that's how you can take each piece and then check in yours. So that's done. Now you can do V1. You can V3 open bracket 1 comma 1. Did you type? And close bracket. You got something? No, you should have type V3 to see what happens on the command wheel.
Z1 to Z2 3 V1 V2 is equal to V1.
Very good. So now highlight from 1 from scroll up maybe. Highlight from 1 through 9 using your mouse. Highlight 1 through 9. I'll give the same trick to you. Highlight 1 through 9. Line number 1 through 9. Highlight. By mouse you can highlight all the way from top. No, the highlight. Yeah. It has been okay. F9. F9. Hope you don't delete it. Save it, by the way. You can complete yours. Everything is good. You got everything. Now go say V3. V3. Just the same variable, whatever variable, and see whether you get 3 numbers. Just check whether your code is working. If you say V3, are you getting 2400 angle? Are you getting that?
I am getting slowly, slowly. When we can, so here it is showing V2 is equal to V1, V3 is equal to V1.
Yeah. But are you getting type just V3? See whether you get a number. You assigned it, but you should get a number instead.
Here I have got, here the workspace I have got. V9,
Yeah,
V2,
type in there to see whether you get V3. Same way with big V.
yes.
Perfect. So now this is working. Now what you do is that you do this. Now you do this. First part input matrix. Done. So now what we do is we need two more matrix. This first matrix is V1. You can actually do not worry about angle. You can put in J in a rectangular coordinate. 2500 plus J0. Yeah, you can actually do 2500 plus 2500 cos 120 degree plus 2500 J1. So now what you do is you do V3 comma 1 comma 1. Do you get V3 1 comma 1, right? You get a number, right? So yeah. So V3 1 comma 1 divided by S load 2 1 comma 1. You understand the and make in a form of a matrix. Don't punch out. Fight. I know you're going to self mobile. And only don't let him help him. So I moved out from the impedance matrix. Everybody is okay with impedance, right? You might have completed it. How many of you have not done the impedance? Okay, so impedance. Still fixing internet. Oh, you have done that. Oh,
Fixing internet.
perfect. So this is the impedance is now very nice. So now you can start doing this one. V1 equal to 2500, 2400.
This is not running for 6 hours.
That's because you have two dots. See, this one is the first element, which is good. This is the next element.
Dot.
Then space. It should work. Try again. So there's a trick. I don't know whether you know this trick. Highlight this.
All.
All of up to, no, from Z1. All of. Now click F9. F9 is here. You need to also get the command in. My number is here. Click F9 one more. Okay. When you run it is coming. Try run again.
Yes, this is coming.
Correct? Okay. Try. F. Oh, it's not. This is a problem. So let us see where the problem is. Okay. Yeah, we got it. Go back. So that I think is a docking step. Okay. Good. Good. Can you move this to the
Now then,
right? Something which is not
use bracket instead of parenthesis. Can I use small bracket here?
this correct. Right. The other question I had is similarly this I, J. Go here and highlight the first one and control C. Right here. Right. So the J didn't like it. So now you do same control C and control V. And then you get rid of the J and say and say I at the end. The other way around. Yeah. And now do the J instead of I.
Okay.
No, same thing. Yeah. That's good. So instead of J and the friend, you have to get yes. Yes. You know how to take care of that, right? Yeah. So do minus and then how are you doing? How are you doing? Not on the top, but the bottom too. You have to do minus minus. Okay.
Well, I have got this high impedances, voltages done. But now I want to go for the first class.
Now the load. Load is that this is S load 1, S load 2, 3, that one.
Oh, okay. Okay.
S load, S load.
Why they can get on this as one yes.
S load 2 and S load 3. Can do any S load. Any variable is fine. Hmm.
What matrix?
Z1, Z2, and V1.
Is V1 done? Can you type in V1 and command prompt V1, small V1. Perfect. Okay. So this is all good. Now you do load. And load is S load 2 zeros and this. Then what you do, you can also do the other one now. V2, type in V2 equal to V1. And then V3 is equal to V2. Now you do load.
My value is coming as 0.0900 and your value is coming as 0.32. I will last.
This is, are you doing current calculation, voltage divided by impedance?
Yes.
That one. Instead of 54.42, you are getting
All your values are totally correct. The last column is
which one?
right. See,
53.12.
they are approximately equal.
53.12 minus 51.
Minus 33 point something, and you also correct.
Yes. Minus 51.
Approximately same, but last value is minus.
Mhm.
If I can find it.
Go back to last. What is it? Something is not correct. S load 3. I load 3. I load 3. S load 3 dot. S load 3 dot.
As V1 is equal to V1 to and
S load 3 conjugate. I load 3 is I load 3 conjugate. I load 3 is I to 3. Yeah, so 0, 75 plus 3, 0 and 0. 0,
last statement.
that's good. Okay. That is S load 2, right?
Yes.
You have to first find S load 3. I load 3. S load 3.
This load 3 is the last value is 13 plus 10 I.
Last value is S load 13 plus zeta. Yes.
13 plus 10 I.
Good.
And when you divide this value,
13 plus 10 I, then you are dividing that with V3. You have to divide with V3.
this is minus 1200 plus 28.46.
V3 is 2400 angle 120. That is correct. 2400 angle. 2400 angle 120 is
Minus of 1200 plus 20.
cannot be. 2400 cos 120.
So it's minus
Okay.
2078.46.
So you did that. Then can you do one thing? Can you do S load 3? Type it on the command window. S load 3. Open bracket. 1 comma 1. No, not equal. S load 3. Open bracket. 1 comma 1. Close bracket. Divided by S V1. Open bracket. 1 comma 1. Enter.
And when we take conjugate, then the answer is 53 point and minus of 30.
Now go.
But the last one,
Go with the arrow up. And now go down here. Here we go. 3 1. Enter.
last value is we have issue in last.
It's something else. It's a 3, right? I don't know, is there anything related to math? Sounds okay for you. S load 3. Can you continue with let me check. I hope that's
We change the load panel, then maybe answer this. Like when I use 113 plus 105, then answer is close to load value. I take 113 plus 110, then maybe answer is close to the
I think there could be something in the load value. That could be possible. But I am not sure whether continue with this. Doesn't matter because the board is right. Put a 0 there and see on the end, not 1. 130 and 100. 130 and 100. Put a 0 then. There could not be any typo for 1. There could be a typo. 9 plus 67. Is that sign correct?
sign is correct.
Negative 9.
Everything is correct. Only the magnitude.
Magnitude 9 plus 67. Something like that.
Compared to all other codes, 13 this order very clear. 137. That's why the button.
One more time.
When comparing with 127.5 and 110 to that 13 is
Yeah. I understand. But I'm saying that it could not be any typo. Continue with that. So the load is done. I put 3. I load 3. Okay, yeah. Yes, load 3 is 127. Yes. And the next is 110. 75. Yes. Entering the good. Okay. That's now. Now I load 3 is. No. You have to calculate. That's it. Otherwise, there's no purpose. The solution is there. So what you do is you write I load 3 is equal to V3. Oh, by the way, did we say V3? I think we did, right? V3. Yeah, you don't need V3, sir. Yeah. So V3, open bracket. You can actually probably do the whole matrix. I'll show you first without that. V3, open bracket. Not equal to. V3, open bracket. 1, 1 divided by S load 3, same variable, S load. Right. Actually, the other way. S load 3, open bracket.
then open bracket.
Yeah, not close bracket. No, V3 you have to close it. V3 1, 1, close, yeah. Then S load 3, open bracket. No, we don't have to make. S load 3, open bracket. 1, 1. Actually, you do it this first. S load 3, open bracket, 1, 1 divided by, copy that, V1 by. And delete that. See and enter that. I mean, can you highlight it? Yes, you can. If it is a script, can you highlight the whole thing? Hold. You click F9. No, F9 meaning F9 the function. Yeah. Is that correct? So now what you do is there is something which is missing, which is the load. As load 3 you have, right? That as load 3, after you put it, after that square bracket right there, up, no, up, not display, okay, before the semicolon, yeah, multiplied by 1000. So you see KVA there, that is it. And then put a semicolon. And then do this again, you can run it or you have to run it. 53.125 plus 33 points. Yes. Now what you do is, you did this, right? You got to do one more work. You got to go before as load 3 and say conjugate, CONG, J, yeah, open bracket. It's correct, open bracket. Then close it. And try again.
F9 or what comes next?
That's supposed to be. And you can continue like that for, so there is another thing which you can do. You can try enter, copy that whole line one more time. And then instead of 1, 1, delete that bracket and 1, 1, the whole bracket 2. Yeah. And then close the bracket. And then put a dot.
There is a bit.
And then try it.
Enter.
Yeah, that's me. Try again. Push it. So if you do that, then you don't have to do 1. See, 1, 1 is for every element, right? You're not doing 1, 1, you're doing everything together now. So what he was saying, 45.833, that is plus. I don't like 53.1. 45.8 minus 30. 45.8 minus 31. Is your voltage correct? Go up and see.
V1.
Yeah, it sounds right. This is cos sign, right?
Yeah. Value of what?
Cos sign.
Which is the or 20.
Should have sign that. 120 minus 120. Yeah. Continue. So you do that, then you go with a do that equation, not that I23
Yeah.
minus I23 is equal to do that to get the current. You should ideally saying this as you have to say here V3 equal to V2, you beat that. Right. So now you can continue with the next thing. Can you check whether it's converging? You continue with that and then see whether it's converging. It's converging. You're not reached that far. Yes, I23 is Y03. Yes, good. You want to go to the next slide?
calculate conjugate. Because my answer is not coming like that.
For the last one, we no,
So I put the conjugate calculate the conjugate. But after that, my answer is not there.
is it SLO3 working?
That's it?
Oh, can you not do multiplied by I? Is it working?
Not good.
Can you do V1?
Yeah.
Let's try that. Not coming. See? So the problem is this multiply. Don't do multiply. Just I.
No, it's fine.
All are I. Just no multiply. It's not liking the multiply.
It's
All the way.
like a right.
Oh. So 2400, that is done.
Everything is done.
Everything is good. Okay. Only your I load is not coming.
Yes, sir. Not that value, but coming.
Oh,
But not same.
oh, that's okay. You continue.
Okay.
Continue. Yeah. Good
My
point.
I not
What is the number you're getting?
that value I'm getting.
That's fine. Continue.
Okay.
You have to multiply by 1000 now.
Okay.
It's multiply by 1000. Yeah. He said the same thing. I think the
But the answer is not same even if it will multiply by twice.
I understand. Yeah. But just for the last line, right? Yeah. Continue like that. See whether it converges.
No problem.
Got it. So then
I did the division there. S load 3 divided by V1 element wise division. I'm not getting that. So it's a difference.
that's okay. I think you can continue. This is good. I don't think there is any, except for 0.1 to the power of E3, I know 3 as per to the power of E1. I know 3. I think this is good. The last one is not the one, right? Other two are okay.
Okay. I did a conjugate at the end you wrote there, no?
Yeah. So my 54.42 minus 34 point, that is coming close. 53.12 minus. The next is minus 51 minus 23.
Oh, somewhere wrong.
There is something wrong. 127, 80, 127, J80 is correct. Yes. The next one is,
This index is right now. S load 3
yeah, that is correct. That is correct.
element wise division.
Yeah, that's perfect. I don't think that's the problem there. Cos minus
One is cos minus 120.
sine minus 120, that is correct. With 100 cos minus 240, I sine minus that is also perfect. And that is good. That's good. 127.5 I 8, 110 plus 75 I, 110 75 I, okay, 13 plus J10, 13 plus J10 E3. It looks like all are correct. I think you're good. Continue. I don't think, only thing is the next iteration, error should be slow. So you just, I don't think, I cannot find anything. Maybe there is something which we are missing, but let's continue with that. So the next is, so this is done, right? So now you can say I23 is the same as this. After that, you can do this for node 2, next node, just this. Even doesn't match on the side, you continue with iteration. So node 2, how many of you have done node 2? Node 2 is done. Node 2 is done, so I have to do something here. So whoever is doing node 2, you can see this slide, node 2 is right here. And whoever is going to node 1, you can do the node 1 by this slide right here, the first calculating the next iteration for 1. By the way, if you use V1, you have to change that to V3. You got it, right? That's 1. So now what you do is you check the previous V1 with a calculated new V1, and then you will see an error. And then ideally, if you are a little savvy, you can put a for loop and then close it, or else you have to do step by step again. At least everybody should be able to go to V1. If you are done until V1, did you do until V1, node 1? Node 1, until node 1, and then you see error between the voltage in the previous 2400 and the new calculator voltage. I12 is not I load 2. I12 is I23 plus I load 2. I23 is the V3 divided by S load 3. Remember that? you calculated the I node 3, right? And then you add that with you understand, right? Yes, just so put that equation there, then you'll go to the next slide. It's time.
It's time, sir. So can we pause here and then we can
Continue on the next one.
resume in the next.
You cannot break that. Hunger is more important. Lunch is more important. Hunger, you cannot do anything without energy. Everything will be closed, right? I mean, also you need energy to get. All right. So what? Yes. That what is 46 point?
It's just a maximum error.
Maximum. Okay. So what you do is that after you get 46, that maximum error, then what you do is you using the new voltage, repeat that, and then try to reduce that. So that maximum error is because you started saying all voltages are the same. Now all voltages obviously are not the same, right? So that error is your trigger or understanding that I need to adjust that voltage. So you use that error, that voltage. So you had a voltage that you calculated with that error. That voltage you have to give that voltage with that error for the V3. Then you redo that back again. Okay, so there is a pause point suggested because of the time. The pause point is basically, we can continue, but the pause point is how many of you have completed one iteration, meaning how many of you have completed getting voltage 1 all that. Very nice. So that should be the place we should be now. So whoever has not reached that place, which is actually only 1 or 2 slides there away, you understand this, right? Let's see here, just to give an idea where we are. So let us see this right here. So let's recoup. Okay, let's recoup what you have done. You have a hands-on experience now, so you should really probably be able to understand. So 2 minutes I'll take, and then that's fine. So let's recoup what we have done. So what we have done is what? Just 2 seconds. I mean, you can continue. So what we have done is we looked at the electric grid, which has got 2 nodes in here, and then we got the impedances, and we said this voltage is known to you. So then the problem is to find these 2 voltages. That's a problem. So that voltages are not known to you. So what we did, we said this voltage is known to you. We assumed there is no load connected. So we said this voltage is same as this voltage is same as this voltage. We know that is not true, but we are starting from there. So we said V1 equal to V2 equal to V3. So then your V3 is known and your load is known. So load divided by V3 is a current that is flowing through the load. So we calculated that current. After we calculated the current, what you did was we used the impedance here, multiply with that current to find the drop and then see what will be the voltage in here. So we calculated that voltage, then you found this voltage back here. That voltage when we calculated, we realized, oh, that's not the one which we said. That we call it as an error. So that is one iteration. So what do you do after you get the error? Well, after you get the error, you say that this voltage needs to be adjusted based on that error, and you use that voltage and then you come back and redo this in a loop again. So at least you did the first pass by hand. You should get a feel of how it's been done. So what do you do with the next pass and third pass? If you are, you can repeat it, which is good. But if you are smart, you will put that in what we call it as a loop. And that loop is generally called 2 type of loop. One loop you can do infinitely, and that is called while loop where you put a while condition or a condition saying that the error between these voltages that you calculated and then one should be less than or equal to whatever some number, and that's a while loop. Or you can repeat this process 200 times or 50 times and see what will so normally you don't go to while loop. While loops are considered infinite loops, which means you spin in the loop and then there is a bug in there, you keep spinning infinitely, you will not come out of the loop when that condition has been satisfied. So you put a for loop for 10 iteration or 7 iteration or something, see whether you reach this small point. So when we come back, you have two options. Not two options, I think we'll see. But when we come back, we have two things to do. One thing is to talk about optimal power flow code. That will be little bit like a show and tell. I will show the code and then I will go through the code and how it's been running and I will show the results. So that's one job. And second job is you continue this in the loop and maybe I can give that optimal power flow code, you can train it yourself. So these are the two jobs that is pending, which we will cover in the afternoon, after the lunch.
Thank you, Professor, for valuable insights. We now break for our lunch. We request everyone to return at 2:45 for the next lecture and hands-on session.
That's okay.
Yeah, after lunch, we will resume the same. Okay, because learning is important part. So if they can do, means you will resume the same thing after lunch.
Yeah. And then after 1 hour, 2 hour, once it's complete, we'll go to the lecture. Lecture will be
चल हाँ यहीं पे रहता है सकता है हाँ हाँ तो हम सेटअप कर देंगे पूरा I'll be here sir
हाई लोड 3 आ गया हाँ इसका सेकंड एलिमेंट, और अब वोल्टेज का सेकंड एलिमेंट जो है आपका ये वाला हो गया -120 वाला, यही डिवाइड कर रहा है। देखिए यहाँ पे ये सेकंड वाला -120, तो थर्ड वाला उसका 120 प्लस 120, वो उसका कवर है, इसी को बोला तो तुमने नहीं लिया। वाला जो था हम लोग कर रहे थे, जो आई लोड 2 ऐसे निकल जाएगा, S2 डिवाइड बाय वोल्टेज तो वही है, फिर उससे ये वाले से हम लोग निकालना था I12, I12, तो ये आई लोड यहाँ से I12 निकाल दिया। उसके बाद एक मिनट बस, इसके बाद जो है यहाँ खत्म हो गया, इसके बाद में ये वाला भी है, ये भी हम लोग यहाँ तक वो बोल रहा था, आप आपको आना है फर्स्ट रिक्वेस्ट बैक, आई लोड 2 जो है हम जान गए, I12 इक्वल टू हो जाएगा I2 प्लस I लोड मोशन। नेक्स्ट वाला जो था, अब ये वाला जो है, अब ये वो this is all done. बोले ना वो आपको check for convergence.
Check for convergence. Acts of evidence. What is it? Greater than 0.001. That's a victim? No, no. अब यहाँ
क्या करें फिर रमेश वाले को चल ठीक ठीक फिर कैसे हमको कह रहे हैं जैसा अभी तुम आ जाओ कल आ जाओ हाँ हाँ बिल्कुल ठीक है फिर थोड़े तो मिस हो जाए
put a square bracket, then you start the first element. When you press a gap, then you say 0.0361. This is the first row. And we check one more time, 0.1520 plus 0.5353i and 0.361 plus 0.2225i and 0.361 plus 0.25755. So after that, you can make the enter. Then you can copy this. So do you need mouse? So I go that's all. I just think that I can start. Did not push.
अंदर ही ऐसा कहीं काम कर रहा है
No, it's yeah.
हाँ
मुझे पता नहीं था. I was not sure. But I thought you took this out. You did not take it.
yes
So I can use my mouse. Very good. Thank you.
you can keep here here
You got where the first row. Nothing. And I'll go when I take it up. So now the trick is you can actually you don't have to type everything. You can take this out. You know, that is the first one. So then put that in there. And then you can officially start when the word comes. Yeah. I was that's why I didn't wear the microphone at all. I use my, this number lock is easy for me. Open the number lock and I can type the numbers, you can type it easy. So if I do like this on the command window, then if I, type it like that, your Z12 is done, right? So if I say Z12, you will be able to get the Z12. So you can translate the DC to a script. Script is basically in MATLAB, it's much like what you are writing is. So you say new, you'll get a script. So this is a white space. It's a script. Which means you are telling that whatever you have written in the comment, you have so how to write this, whatever you believe, the command window, how to put it as a code, can actually go there and you can look at what you have done there. And you can come back and see this. You can just copy just like that. And then put the right piece in the form of a script. So you can test it out or come on with the here. This sheet you can, as soon as you go in there, this sheet you can say, say as, and you can say my forward backward smooth power. So I can put in the folder, environment, you can say then forge, and I can get them. Now this is a code. And then you can do some things like, for example, see where it's seeing, here are these are some of the things that you should write when you write a code. They are always clearing out. No normal coding. Definitely, expensive events. When you write question. So your first Z12 is done. So now I can actually copy this. And then sorry. And what I do is I also make sure I write like this. And I said, if you write anything with percentage, it comes as a command. Comment. So it's not a comment. I'm making both. What is all of them? Because in future, Z1 to Z13, so I know that is what I'm doing. Some people also do something like this, which is basically to show like the boundary. Please, so again, one common and it's starting to know what that we need to write on job to I'm starting to realize that without them, I cannot move. So now they are there. You're actually waiting and saying that we cannot go live or rather online without you. So you are the, what is that called? Guiders for us to move. So, I think, we'll just continue. Uh, so now here you see so if you have done with this now, so you may ask the question. That's exactly the question you are asking. Is they are same, right? So, can I change? Yeah, I mean, now you can change. So you can say 2660 and the next one is 9368 and the next one is 0632. Then you have 5664. And then you have 0632. And 4816. And this is 1 3. So I copy 1 3 and put that into 3 1. This is 1 2. Then I put that into 2 1. And this is 3 2. But that's pretty same. So I copied the 3 1 and I changed it. And this is 2 3. So that will be the same as 3 2. So now I have 2660. I copy that onto this one right here. And then I have copied this onto this one right here. So within a fraction of maybe 30-40 seconds, your matrix is done. So these are not very hard. Just to mention. Continue with the second round. Just helping and starting people who have not done. Any questions? You're good, right? You can do the second iteration. Hmm. Hmm. So error will keep going down, and then you can stop when. Yeah.
My question is how I will get the error equation, because after solving I get the matrix V22.
So you did after V3 you calculated V3, right? The V3, and then after V3 you calculated. You are backing calculating the V1.
The last line, sir.
So this node, so this is done.
Yes, sir.
So once you are done with the node 1, now you are going to find out the difference between the V2 that you calculated first time and then V2 calculated next time. And that's basically your error, I mean, whatever you call it, error, maximum.
I have calculated V22, just above that line.
So V2K plus 1 is V1 minus Z12 I12.
I have calculated that.
You did that? Okay. So that V2 that you calculated, V2K plus 1 is V22. The one you are calculating is this.
Yeah, I have calculated that.
And then you have the V2 that you have already done from the first iteration.
Okay.
So that V2 from the first iteration is
maximum value.
is this. So what we did was we 2400 see 2400 0. We said 2400 0 is the voltage on all the buses. So all that is actually our guess, right? I mean, we know it's not true. So you 2400 that is 0, you are putting in V1, V2 1 and V3 1. That V2 1 is 2400 0, right? So V2 2 is new that you can. So you get an error between V2 2 and V2 1, which was 2400 0. From the next iteration, it will not be 2400 0. This will be the new that you calculate. So you got the V2. That is what we call it as a V difference. You see that? Understand, right? That's the error. Now that error you are not taking anywhere. You are not adding anything with the error. That error is just to check whether you want to stop or not. It's just a stopping criteria. So what will you do to the next time? We know that we cannot use V21 because V21 minus V22, the error is not 0. So what will you use? We will use V21, V22. And so you use 76, that matrix to update the next voltage. So for example, you take that number, they take that number and find the drop to get V3. So first we said V1, V2, V3, they are the same. Now you are getting new V2 and new V3. You should do it. Don't leave the code. Go. So after you do the first iteration and the second iteration, you will be now getting new values of V2 and V3. Do you have new values of V2 and V3? Not exactly the same number because of it, but you have two new values of V2 and V3. Yes? How many of you have new values of V2 and V3? New values of V2 and V3. V1 and V2 and V3 was 2400 before. Right now, V1 is 2400, V2 and V3 should be different. If you have gotten new values of V2 and V3, you can raise your hands just to get a check. Not yet. Okay, take your time. Oh, here's the thing. MATLAB takes radians, not degrees. For him. MATLAB takes radians, not degrees. So when you say cos 120 and J sine 120 for the voltage, you have to convert that 120 into radians. You did that for the first iteration. That could be the problem in the number. Carson diagram could be still, you cannot judge it like.
Right.
2 radians are actually pi divided by 180. So you do 120 times pi divided by 180, and I'll try here. So I just thought about it now. So could be the reason. So you did you get V2 and V3 also. Oh, very good. That is it. It's going down. So the winner is here. There was a race, and unfortunately, whoever was leading first is going down, and the winner is, I don't know names, but the winner is the group here. And you can continue on the third iteration. I mean, do you want to try put a for loop and see? I don't know whether you are interested to try a for loop. You could do for I equal to 1 to da 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 and see whether just if you want to try, you can try. Or you can
possible, then do the magnifying. It will be visible to all.
Oh, so, yeah, that's okay. I'm just playing around with that. Okay, so second iteration. I think you completed second iteration. Anybody else has completed the second iteration? Not converging, it's diverging. Error is increasing, error is not decreasing. Error is increasing, decreasing. So 1 to 1. If the diverging group is more, then I will intervene. Should be some bug. I don't know whether. How many of you completed the second iteration? Oh,
Like define red 1, red 2, red 3. So radian to convert it in radian, then V1 equal to 2400 cos Z1 plus sin Z1 into I, and then V2 and well, Z1. Good. Now V2 equal to V1.
and make sure you are consistent with notation. You have a big V and small v. So V3 equal to V1. think V is yeah. When you calculate the based on the load and the voltage, calculate the current. To have the load also. Similar. Plus minus 120 plus sin minus 120 J cos plus 120 plus sin. Yeah, I think the 120 MATLAB don't like degrees. MATLAB only like radians. So you have to convert 120 to radians. So 120 is equal to, in radians, is equal to 120 multiplied by pi divided by 180. So you can write something here. So what I did there, I call it radian 1, just, for is equal to 120 times pi divided by 180. And I call it radian 2, minus 120. Oh no, a minute. One is minus 120 times pi divided by 180. Make sure it is consistent. So this is we call it radian 3. So now I can do cos radian 2 sine. We don't want radian 1, right? Radian 1 is 0 because you already know 2. Then you can say radian 3 and sine radian 3. So now we are consistent with converting into radians. So your V1 is done. So now you can go and then say V2 equal to V1 and V3 equal to V1. And now you can start as the load, write down the loads. There are two loads as the load. Yeah, as the load. Uh, so there are two loads as load. You can see, right? You want me to zoom in? Zoom in? So if you are, how many are done with second iteration? Second iteration not done. Second iteration. You want to go a little further and do third iteration. Just take it easy and then. Oh, 10 minutes for the second or third. Not very bad. Then that I don't know that it's what I mean. Oh, that's a nice idea. We can put that into for loop as an assignment. Let's see how I can challenge. And I can guarantee that if you complete that, you will get a credit for your third semester power course. If you don't do it and then if your computer course closed, then you will not get the credit for in the third semester. If you do it now, we will tell them give credit to the third semester. You don't get power course you're going to take, right, in the third semester. Yes. For that, you should show that you can solve power flow. There's one thing which we always say that you should stay away from. That is your tendency to not to do things. Keep doing. You should not stop. Well, I tried to do this. Okay. Second iteration. Still working. How many of you have completed second iteration? It's going down. You want help?
We have initially V1 equal to V2 equal to V3 equal to 2400. So, then this voltage is 2400 plus I into Z. It will be greater than 2400. Then it is also greater than 400. If 400 just fastest after the third iteration, we got value of 2437. Again, when we assign this to here, then the value got increasing. So we are not
Not assign that here.
we can't.
No. So this one made this high, right?
Yeah.
2437. So you are actually wanting this voltage, right? So you have two options. You have to keep this voltage constant or this voltage constant. Yeah? If you want to have this voltage constant, this voltage has to go down, right? Then only you make this voltage constant. So what you do is that you look at this voltage in here instead of 2400, that will be down, right?
Yeah.
So your 2400 has to be here, not here. So you use the 2400 here to calculate this load. That is why this is going up, right? Understand? So this has to be down. So whatever you are seeing here, if it is up, you have to decrease this voltage. So what we will do is we will we have well, I think only one option, not two options. So we will give this as a take-home assignment for you, which you can solve because you already got an idea what to do. So try working with MATLAB and solve it and then bring it back tomorrow. How many faces are liking that? Some faces are saying, let's try. And what we will do is, if you have done this 2 iteration, and if you are excited about it, you can start putting that in a for loop. But this is actually, there are two purposes for it. One purpose is obviously trying to see whether you can complete an assignment. Number two purpose is, if you are in this area, this is a must, meaning you have to work on some level of coding in MATLAB, not necessarily this power flow. Any power flow you must do. It's a fundamental thing. So I remember when I was in the master's program, I did my assignment was developing power flow, scaling it up to 1000 bus. Then you go optimal power flow, scale it up. Then you do transient stability analysis, scale it up. This is actually a part of, I'm not saying that you should do all of that, but at least to get an understanding of how to freely work with the MATLAB. So it serves two purposes, right? I agree that I can. So that's something which you will do. I will turn your attention to next 30 minutes or so, or maybe another 30-45 minutes or so. I will turn your attention to optimal power flow. Okay. So there are two parts that I think you should be doing as a must. One part is to solve the power flow which we are giving as a distribution. Another part is solve the power flow for transmission system using Newton-Raphson. I gave you an example for a 3-bus system. Then the third part is to solve the power flow for transmission and the distribution system combined. What we call it as the simulation for integrated transmission distribution. So those 3 assignments are actually ideally you should do. So you'll get a good grip of what you should work on. But as a first step, you can dream about it, but as a first step, let's do this forward, backward. I think this is pretty reasonable, right? You understand how to do it. It's not that big task to do it. Yes, agreed? Okay. So what we will do is I will show you something on optimal power. So optimal power flow, we learned about it this morning. And optimal power flow is basically doing power flow in a different way. Remember, doing power flow in a different way. How do you do the power flow in a different way? You run power flow through optimization routine. Okay. So in the morning, we talked about the main pieces of optimal power flow. Optimal power flow consists of optimal power flow modeling consists of an objective function and the constraints. And constraints can be divided into equal constraints and inequality constraints. So, and then we said that we have optimal power flow can be solved using mathematics solver. One way of solving is by using linear programming, where you run the linearized version of the power flow equations. Then you can run it through nonlinear programming, where you run the power flow equation using quadratic equations in that form, or higher quadratic equations. And the third one you run through fixed integer programming. That's another way to do, but you also run through what we call it as convex optimization, right? So what I am going to show you is some small way of running the code for a small system for an electric distribution network. So this is an electric distribution network. This network is a part of an IEEE. Okay. How many of you have heard of IEEE test systems? Few people have heard. Very good. IEEE test systems are systems that academics uses in general to study an electric grid model. They are systems that is developed by a group called IEEE, it's Institute of Electrical and Electronics Engineers. They provide power grid models that you can use to study analysis of power grid. It can be power flow, it can be optimal power flow, it can be dynamic and tension stability assessment analysis. These power grid models are actually not fictitious. They are real power grid models. The real power grid models are modified or aggregated or reduced, keeping the characteristics of that real life system and developed in the form of test system. So which model and which part of the world these test systems are available? You can see that by looking at the IEEE test system library. IEEE test system library, you can Google and search IEEE test system for power distribution system model. You will get a link which has got a lot of test systems that you can use to study power grid model. So these test systems are characteristics test system to study specific phenomena, right? For example, oscillations, dynamics, things like that. So when you are trying to develop a problem as a project or as a research project or something, you first use this system to test these problems. Some of you are maybe aware of this or some. So IEEE test system for a power distribution network, one of an unbalanced IEEE test system which normally we use to study electric distribution network, is an IEEE 123 node test system. 123 node test system consists of a substation like LTC, regulators, and main feeder and laterals. There are several nodes in the 123 node test system. 123 node means what? The test system has 123 nodes. That is why it's called 123 node system. This is a subset of the 123 node test feeder starting from substation. So this is a substation. This is a load tap changer transformer. This is a switch that connects this where the feeder starts, and the feeder goes all the way like that, 120 test node. This test node, we have some of the points where you have connected PV farms. Okay, so these PV farms are connected to study the IBR integrated distribution network. So you can study that distribution network like that. So the first 20 nodes from the IEEE test system is extracted and shown here, which are 5 PVs are placed. 50 kW on bus number 5, 70 kW on bus number 8, 100 kW on bus number 13, 150 kW on bus number 15, and 50 kW on bus number 9. Okay. So you say these are placed. These are placed means what? You place them. How do we place them? We'll talk about it. Because go ahead.
How the numbering are done, like what?
Good question. So this okay. So there are I'll tell you some. So real life electric grid is probably here too, but real life electric grid doesn't have numbers. It has only names. So for example, whatever the names we have, Prayagraj, 1, 2, 3, whatever. So when you study a power grid network to study for power flow, you cannot use names. You have to replace the names from into numbers. So what you do, we call it a bus numbering system. Now, why you want to do numbering? There are 2 reasons for doing numbering. One reason, if you get the numbering, you have an idea about what are in sequence, like from substation all the way to the end, what numbers are in sequence. Second thing is, if you want to run an algorithm for power flow, for example, you have to run in a for loop. You say 1 to 35. You cannot run 1, 17, 55, 30 or so. So this is called bus numbering. Who does that numbering? Basically, we does the number. In real life, there is no such number. IEEE test system will give you numbers in a sequential form right from substation to the last point. So these numbers are done from substation to the last point by the test feeder system itself, which means you can just borrow the test feeder and run it with numbering. You don't have to number it. What happens if you have some numbers given by somebody or names given by somebody which is not in the order? Then you need to run an code through, we call it the bus renumbering or bus numbering code. So what does that code does? Code actually scans through, if it is even a number or a variable or a name or anything, you can run code like, for example, C or MATLAB using a function called fscanf, which is basically a function to scan the image, and then you can create number out of it. Long story short, this is has to be renumbered from 1 through 123, and that's done by the test feeder itself for this system. That is actually because it is numbered based on distance, actual distance. So that is done through the distance will be more. That is why it is there. Yeah, physically, right? You don't know because it's drawn like that. It's that is, you cannot judge that. You draw, you can redraw in any way you want. You can make this longer or shorter.
And it's
Hard to.
Indian northern region, there is 273 bus system. So buses are voted in terms of numbers. They are actually places, as told by sir. So 273 bus system is a very large system. So in order to just analyze the change in number.
Answer renumber and change. So you cannot correlate. Suppose you are thinking, so you did not probably think through all what I am talking about. You are thinking just looking at this, see why that is nearer and why that is far, which is also a good thing that you're thinking like that. That you must think. And we also think like that. So don't worry about that thinking. But what I'm saying is, it's very hard to understand from physical appearance that whether it's near or far. So what you do there is you do But I'll come about that later. So there is something called, you can do a search, depth search or breadth search based on a distance, and you can actually get number based on that. So we'll talk about that later. So this is something that you have sitting there. So MATLAB has got a tool called live script. Live editor or live script is a tool that you can use in MATLAB to live talk about how the code runs in MATLAB. So what we are going to show you is two things. First, we are going to show you how you model the system. I don't know whether you can you see at the back? Can you see these numbers? No? No. But you don't have to, you have to, so any system, you organize the data of the system to run the power flow in two forms. One is called bus data, the another is called branch data. Bus data is to give you the bus number and what is in that bus, and branch data is to represent how the branches are connected. So this is something called branch data. Branch data, everybody know bus data, branch data? I think some of you already know. Okay. So branch data means that you connect the bus or branch between buses, and you see this branch data consists of from two, node 1 to node 2, 1 to 2, 2 to 3, 3 to 4, 4 3 to 5. These are node connections. These are resistances. AB, AC, BB, BC, CC. So you have resistances. You also have reactance values. For the resistance and for the branch. And then you start having bus data. And the bus data, you will use the QL. PL means load. You see load information. You can also the PV. PV means photovoltaic. And you see the PV load. So you said that I have put to the PV implies the PV. What am I doing here? Saying that the PV is there. I'm going to put the capacity of the PV right there. Good. This is how we do the load data and PV data. Do you understand what this is? I will let you read through rather than me speaking. Some comments are there, so you should be able to understand. What is that? Do you know? Can you see? Can everybody see?
This voltage is very
What is base? What are we doing there? We are converting everything into per unit basis so that you can actually use the run the system without having. So that's what that part is. So then you start representing this in the form of a graph. So if you put it in the form of a graph, you will get a
what's the unit of heat? What the unit, like suppose it is 100. So it is 1 kilowatt.
Yeah, so that is something you can actually represent. This is basically in kilowatt. So what we have done is you can utilize the data set and then represent in the form of kilowatt or watt. Depending upon the base, you can make the kilowatt and you can make the watts. If you have a 1000 MVA base, you write it and then you put the number there, then it will be 0.5 per unit based on that. So basically the load and the PV, the data that you are writing is whatever the kW you write in that values. So it's 40. So there is a little bit of, it's a very good thing or question or comment also. There is a little bit of creativity you can use here. You can utilize whatever way you want until you get into per unit system, depending upon how you want to think about. So modeling wise, you have some flexibility. Now this represent how to generate the, based on the from bus and to bus, how to generate a tree-like structure for the distribution network. I am not able to discuss the code and then run at the same time because I have to move the screen. I will run and then I will show you how that thing looks like. The next one is, so these are defining incoming and outgoing branch. So you have to run, if you run a code, you have to provide incoming and outgoing branch connections. Right now we are hard coded it, meaning, everybody know hard coding means? No, okay. Hard coding means putting a number and then using that number for your purpose. So that's basically based on case to case basis. Okay? Generalized code means, so for example, if you go, okay, V3 is S3 divided by, then you say V2 is S2 divided. Okay, next time V3 is V3. So these are hard coding. But if you put, okay, 4 I equal to 1 to n, V3 is, that is not hard coding, that is generalized, basically. I think I mentioned about it. So there is a word that it is hard coding, meaning just putting constants and number there to run something. Hard coding is not an effective practice in general, but hard coding is very good for troubleshooting. Otherwise, in a scaled system to do, you cannot know what's going on with it. So these are number mentioned, which is kind of hard coded. So now you have to mention the, you have to put the impedance matrix and H matrix. H is something that in convex optimization, we call that as a Hermitian matrix. So you might have seen this word coming while I am talking in the theory. So you have to develop a Hermitian matrix to move it in the form of convex optimization. So the H matrix equation you see here. Why am I showing this? To just show you that whatever math that we did in the morning and talked about it, same thing you are converting into code. Nothing fancy here. So the H matrix that you have has a math like that. So I cannot put the slides and the code and the result all in one. But if you look at the slide that I discussed, I'll go through that. You can look at it. This is the equation for H, Eij and Qij, Hermitian matrix for P and Q. So you can actually represent that Hermitian matrix in the form of math that is written in here. This thing 2 times R, 1, that is basically that right here. So you can write code. So I'm not going through that code part, but I just wanted to connect you with what each part looks like. Now we can actually have a load PV information. Load PV information is basically to tap what are the values of the load and what are the values of the PV. So this you will get a little bit more clarity on some of the questions that we have here. So this is a P load that is taken from the node ID 1, 2, 3, which is written on the top. Then you can actually get that load information and you can change the load like a multiplier. So for example, if you have a multiplier 6 PMP1, you can actually have a load change. You can also get the PMP in here. And then you can multiply that load into base MVA, 1000 and kW depending upon how you are representing the load. So right now it is in kW form, so you multiply based on that kW. And then you can do a load apparent power, and you can actually size the inverter. So I don't know whether you remember or not, the inverter reactive power is calculated based on the load, I mean the PV load. Q is equal to square root of S square minus P square. You have a equation that we discussed. So you can actually use that equation in here, and you can also rate the inverter size more than the PV capacity. Okay, depending upon how you want to put the inverter. So now we have completed setting up the system information or the electric grid information. Now what we will do is we will start writing the code in optimization form. So somebody was talking about optimization routine, and they were asking me, or rather I was asking Paresh, I guess, was talking about it. So I was telling him about using optimization and optimization solver. So optimization solver, actually you buy or you get some license. Some of the optimization solvers are like, Cplex and some different type of solvers you buy. And there are some optimization tool or software that you can run, which is, some of the software are pricey. So I think he was mentioning he's using GAMS. GAMS is, I think, pricey software. So there is a tool which can be used to run optimization in MATLAB, and that toolbox is free. So you can download that toolbox free of cost, and the name of that toolbox is YLMIP. Okay, so if you go to search, I'm not going to digress it from here, but if you can search for YALMIP, you can get a tool developed by one group which has got an installation software that you can install, and that YLMIP installation, if in the same, it runs in MATLAB. So you can run several solver in the YLMIP tool free. YALMIP. YALMIP is the name of that toolbox. So that you can download it. It's a zip file. You unzip it, put it in a path in MATLAB. You can run many optimization solvers are free, except for some of the optimization solvers like Gurobi. Maybe Gurobi is also free. I don't know. So try the software. CVX is another group that is only used for SDP kind of a software programming. CVX is okay, but CVX, I think you have to, if you run a long code, you have to upload it to somebody and they will solve it and give it to you, or something like that. So it's a little tricky. This one is you can use. I suggest, we had a lot of fun with this tool. There is a other tool software, optimization solver that is not available here. You can get academic license. I think one or two, either Gurobi or some is not available here, but you can download. Yeah, so you can go to YALMIP and then get it. Okay. Yeah. So we can talk about it and we can use it We'll talk about it later. But just so if you do that, you will get a optimization variable can be used using this function called SDP var. SDP var, you can write to the node voltage, complex branch flow, slack, power bus, and PV reactive power. So, and you initialize that, and then you're ready to run the optimization. Okay. So, what is the optimization that you can do? You can solve the optimization using an objective function. This is the objective function, sum of voltage deviation of all the buses and the phases. So, this is the objective function. So, this equation is written here. So, the next equation for the constraints is the power balance. So, this is power balance equation. So, constraints can be written for the power balance equations. So, you can actually write power balance, voltage drop, and voltage bounds. So, you can go ahead and then develop the constraints for power balance. So, this is a constraint for the power balance. You are writing the constraints independently for each node. So, this one doesn't have an upstream branch, this one no downstream branch, so you write that. And so, every node you can write it to do the constraint for the power. This is a constraint for the inverter reactive power limit. This is a constraint for the voltage bound. You see the constraint 0.95 to 1.05. And constraints for each branch, you can actually do the voltage constraints for each branch. So now our constraints are done. An objective function is done. Is that speed okay? Do you understand? I'll stop here and ask questions. Any questions? You understand? We can, but 20% are normal because 100% is actually almost double the cost. Normally, people try to overrate the inverter a little bit, not beyond that. So that's why I kept it as 20%. You can run for any number. It doesn't. Real life says that reactive power support that is required in a specific node by any device is 30% times the active power flow. 20 to 30%. It's just a rule of thumb. It's not. So we are ready to solve. Solving optimal power flow is optimizing with constraints and objective function. And these are the voltage that you collect. So what do you get? How do you solve the optimal power flow? You solve the optimal power flow to find out for an objective, right? The end you collect the voltages and you plot the voltages and see what is that voltages. If the voltage is not bounded, that means the solution is not feasible, whatever you are getting, right? So the indicator is basically the voltage. The voltage is plotted in here. So now you plot the voltage, you have a challenge. The challenge is unlike transmission system, when you plot a voltage, you will not get voltage in every node. So if you have suppose 3-phase node, you will get voltage in all the 3 phase. And you represent the 2-phase lateral, you still need the 3-phase nodes to represent the voltage. So one phase is not existing. So you have to put some number, otherwise it gives MATLAB gives an error. So you put an NAN or some number to represent. So you see a bunch of those kind of things in here for each of those phases. And you can compare that with the base case. What do you mean by base case? You can run an optimization algorithm or optimal power flow without having any objective function. If you no objective function specifically created or zero objective function created, the optimal power flow should run much like a power flow. You should be able to get the results from the power flow. The methods are different. One is optimal power flow, one is power flow. They're not physical laws are not abided. You're artificially creating physical laws in optimal power flow. So you want to make sure that it is exactly the same as a power flow. So that's another benchmark you do with optimal power flow. So base case situation means that you are trying to run the optimal power flow without any objective condition. You just see whether it satisfies with power flow routine. And then you can plot. So now we'll do two things before we go to run this. One thing is review one more time your optimal power flow routine. So you can see that the optimal power flow we talked about the three different variation. One is when the losses are ignored, and that is called linearized power flow, linearized distribution power flow. Then the next one is you can run that through relaxation models. Then you have two convex part. One is semi-definite programming, and the last one is the second order cone program. Remember those three? Okay. So that being said, we will now go and look at the how to run. So you can actually run this, what we call it as a live script. So if you run it as a live script, you can run in different places. You can click the run button in here. So the first diagram that you will see here is the branch. So you see the branch, how that are connected based on the branch representation. This is the connection pieces for the optimal power flow. Good. Can you see? Okay. All right. This is basically the branch connections, and you can say you can see whether it's successfully solved. Yes, it is successfully solved. This is a solve time. This is actually the time that is taken by MLMIP, and this one is giving that successfully solved with a solver called linear programming, and the element wise distribution of constraints. Other constraints are be taken, and coefficient rating associated with that. These are some metrics for the OPF, and you will be able to see the performance by looking at the voltage profile for all the three phases for the 20 bus with and without the optimization and comparing. GAMS. Yeah, we can use MATLAB optimization toolbox. You solve it using MATLAB optimization toolbox. But MATLAB optimization toolbox is very restrictive. It is not a convex optimization toolbox. It is more like a generic optimization, linear programming, non-linear programming, that kind of toolbox. What we are doing using this tool in LMIP is to solve through using convex optimization. So convex solvers, it's like a little bit more math there, but in general, convex solvers can do things to convexify the equations that we are giving. For that, the solver has to really understand the equations and then convexify. And that's not possible using MATLAB. Many solver in MATLAB. There are several tools. So convex optimization toolboxes are very few. I think GAMS is one of them. CVX is one of them. The LMIP is one of them. These are toolboxes. Toolboxes are different from solvers. Solvers are generated by companies like a Gurobi, Cplex. Tell me some names. I'm blanking out some. Cplex, Gurobi. It's only two things you know. There are some 8 or 9 or 10. Or yeah. So GAMS, LMIP, CVX, they are toolboxes. They are not solvers. Solvers are solvers, which actually solves optimal. I think there are 8 or 10 of them, which are convex solvers. Non-convex solvers are many, like linear programming, quadratic programming, sequential programming. So SQP solver, all those non-convex solvers you can use in MATLAB. So there are convex solvers. There are, I think, several items, not just Gurobi, Cplex, or a few others too. Just to give you a landscape how that is done. So this is similar to that. This is a convex optimization for that same feeder right here. It is done through SDP. So this is the line info. That line info is completed in here. Then you have per unit conversion, connectivity matrix. You have modeling of regulators. Regulators are modeled with the tabs, which you can see right here. Then you can define the variables, complex power, Hermitian matrix calculation, active and reactive power calculation, minimum value, maximum value, and now SDP. So the same problem, same power grid that we have for solving, now we are solving through SDP. SDP is semi-definite programming. So you see the equations for SDP. These equations are actually the same equations you see on the slide. So you will see the constraints calculated for each one of them. And SDP constraints, you will see that is written here for single phase lines. So every line you are writing the constraint. Then this is a power balance equation. So you have a line power balance equation written for every line. Voltage constraint for slab bus. These are the voltage limit or bound calculation for every line. Power limit calculation for every line. And then objective function. Objective function, my famous solver, Mosaic. That is the third one which I'm adding to your list. There are, I think, I said 7 or 8. Mosaic is the one that is used for SDP solution. So you see the SDP cost is loss, constraint, loss, SDP setting, solver, and mosaic. So you are going to solve this using mosaic solver after you set it up. And the objective function is cost, which is loss minimization in this case. So now to minimize the losses, you have to calculate the line losses. So this is line loss calculation, calculating the substation power flow and plotting, and then plotting results. So this is SDP. So you will see the branch data, and then you see that this is not solved because you didn't see the solver mosaic. So the system is not solved. So if you want to solve this SDP, then you need to install the solver mosaic. Mosaic is actually not a part of YALMIP. I think you need to buy it and install it. So that is what it is. It looks like I have not installed it in this laptop, but you can run that. So let's see if I can run the other one. This is the second order cone programming. Another solver, now the fourth one, is called cone PROG. It's called cone PROG is used for second order cone programming solver. So the cone PROG solver is available in here. So solving cone PROG with the solver time, optimal solution reached for the because of the after a successful solution from the solver. So you can see in the SOCP formulation. This is the SOCP formulation. It's basically coming from the what. So in the SOCP formulation, you can actually see constraints limit for DER, voltage drop constraints, power flow constraints, extract constraint, and so forth. And you can see that the with and without DG, how the optimization value is doing, how much the power loss has been reduced with the optimization solver. You can see it. So I'm doing this most like a show and tell, so you will understand what we have done and how to model that in the convex optimization. So I'm going to stop here and ask. Oh, I wanted to give credit to a couple of other group members we have in our collective group. This part of this optimization work is also available in IEEE repository. It's called, we conducted an IEEE tutorial on the optimization with two other professors. So it's teamwork, and acknowledgements are in here for those team. And if you want to do more detailed understanding, you can also refer the tutorial that we have, which is free of cost if you are an IEEE member. I don't know whether, I think most of the people are IEEE. So you can go ahead and search in my name, optimization, convex optimization tutorial, IEEE PES. And if you go to IEEE PES, you search for convex optimization tutorial. So we have a 3 faculty member group and few students together. You can see that this is not a one-person job, so we have developed together. I will give you some part of this also, not this, but the one which I developed my own. I'll give you a part of that for you can use it as well. So you can distribute it for a small system. But I don't. If you practice, then you will be able to see it. But I don't think you can build it here because it takes some time on the convex optimization. But I think the other power flow you can they can run it as an example. Any questions? Any thoughts? Yes. Go ahead.
Yes, here the losses reduces just half. Yes, it reduces means half. What other optimization one can use to reduce more losses? This recently,
Along with the losses.
this,
So this objective function is just losses minimization, right? So that loss minimization is the objective function. It is minimizing the losses. Now, can we use another method or another optimization
question
to
is
reduce
we
more
can
loss?
reduce more losses further with the other optimization. Means where
So
we can
convex optimization is global. If it is a global optimization, you cannot reduce the losses beyond that. That's basically the global optimization. So it claims that it's globally optimal. So it's obviously making it global optimal, finding the global optimal point. So you cannot, you will not be able to get beyond more than this for that. Well, so there are so you're talking about objective of loss reduction. Losses can be reduced by several ways. Losses can be reduced on an existing system just by changing the set points, which is done by optimization. So optimization doing its best based on the existing system. You can also reduce the losses by having photovoltaic in every place, which can supply the load good in all the places. So what happens if you have a photovoltaic here and it supplied the load there? Another photovoltaic here, supplied the load there. Will there is a need to have the power come from substation to those loads?
Yeah.
If the power is not coming from substation to the loads, what happens to the loss?
automatically reduce.
Can you make the loss zero if you do it every in local point? Yes, you can make the loss. That is not a part of optimization. That is a part of having resources allocation in different points. How do you arrange the resources allocation? Can you ask the photovoltaic to do that if you are having existing photovoltaics and do the best? You could do that. You don't need optimization for that yet. I mean, some level of optimization is something different. So there are different strategies to do this. But as far as given problem is concerned, if you are using bunch of optimization tool, convex optimization is considered to be, if you do it well and you have a feasible point, it will give you global optimal point.
Yeah,
Which means you cannot
for
that
same problem.
that is it. Yeah. Well, you cannot do. Yeah. So if your question is that the only way to reduce losses? No, because there are some other ways to reduce loss. You understood that. So this actually gives, so SDP does pretty similar close by close results as opposed to SOCP, which is another way that you can use. So that is why people talk about these kind of optimization technique. Even though you can see the intensity of math there a little bit, you might have gotten the taste because it's not, you need to really understand some of the things which I cannot even. So what is a Hermitian matrix? What is the property of that? How do you develop? That's actually a course or this optimization thing itself is a course by itself, right? You cannot, so if you want to go deep in that. But what our goal is for this GIAN course is to give you a flavor of what are the things that you can, so you touch base with. So we are not going very deep in each topic if you may look at it that way, right? That is the whole idea.
So what are the fundamental difference between nature-based optimization as well as normal?
So if you are looking at, for example, swarm-based optimization, or there are what is the other one? GA, genetic algorithm based optimization, all that. When you are doing those type of optimization, we call that parametric optimization. Parametric optimization is a method that is done just by optimizing the parametric space. Okay? That optimization do not know about electric grid, do not know about physical constraints, do not know about nothing is modeled. What is just modeled is taking the parameters, finding out an optimal phase for the parameters. Now the generation of that parameters is up to you, how you generate the parameters. Can you generate the parameter using a power flow? Yes, you can generate the parameters using a power flow. And you can say, this is the parameter that I generate. Now you get this parameter into point from one point to another point which you consider as optimal. So that black box or whatever that soft computing method is going to give you a parametric space, bunch of parameter in this space, finding out the best parameter given a condition and then giving back to you. So that is a completely software that is not knowing about physical property of the system. If it is for used for optimal power flow, if it is for energy market, if it's for anything, they are just using the parameter and optimize. That's basically what the soft computing methods does. So that method, because of that nature of that method, those methods are not mathematically involved, in the sense that those methods are not writing the physical equations of the power grid and writing all the equations and conditional laws of the power grid. But they are challenging in a sense that you need to find the optimal value in that search space. So in that level, it is important, it is challenging.
Sir, one more question from my side. Considering the equation.
Yeah. What should be the property of a good optimization method? Because we may use different optimization methods. When suppose for optimal power flow, what should be the required property for a good optimization tool?
Required property of the code optimization tool.
Yeah, optimization tool. Because suppose everybody is claiming that my optimization is better than other optimizations.
Oh.
So on what basis we can just decide this particular fact, that what should be the property of a good optimization tool, so that I can pick from the beginning?
So the very good question. So as far as a physical power grid, for example, is concerned, when you are going to look into the end result, the tool should be able to give you the end results considering the real life scenarios. That is basically should be the best property, and then doing the best job considering that scenario. So for example, if you are going to use a tool, a code or tool that is actually, so there are different pieces in an optimization optimal power flow method. If we are using in this way, there's something called a tool, there is something called a solver, and there is something called a model. So these are modeled based optimization. Now if you are using a parametric optimization, there is something called a tool, there is something called a parametric search space, or maybe sometimes a solver, sometimes even not a solver. That's parametric optimization tool. The model based optimization tool, there is a model, there is a solver, there is a tool. For example, all the optimization classes which you have a model based optimization belongs to that category. Parametric based optimization is just a parameter optimization. There is no model associated with it. It can be used for any system, like process system, or anywhere you can use, particles optimization, things like that. Any tool that you are using for optimization, that tool by itself and the solver by itself cannot complete the job. You need to have the description of the process or the model. So the requirement for the tool for us, for example, in the power grid sense, it should satisfy the power grid laws. It should satisfy the power grid constraints or power grid setup, and it should give you the best optimal results for that specific problem. That is the best tool, best framework. I don't want to use the word tool because tool, solver and model together you call it as a framework. For that to happen, you need three parts. All the three pillars are important. One is you need to have a very robust model. That model takes care of the physical laws of the power grid. So for example, you need to have a constraints, voltage constraint, power constraint, thermal constraints. All those things are a part of the model. The second, that same model should be able to translate the power grid into the tool, and the tool understand that translation. So for example, power equations, you are translating that into cone equation. The tool don't know about anything about power equation. So all these things are done by model. So what we have to do is basically develop that model and make sure that model satisfy electric grid on one side, and the other side translating that language to tool, the tool can understand. So that's what we call it modeling. And after that, the tool should be able to solve that problem using a solver, and the tool should be able to get a result that is possible to get a result. For that, the tool needs two things. Tool has to get a result in combinatorial time, which means you don't get the result tomorrow. It has to be done in whatever. Second, the tool should be not be giving infeasible, meaning that some got stuck, it's not solving or something. That's the tool's job. Model's job is to make sure that whatever results which is coming out is making sense to the power grid, like voltages are within the limit, voltages. So a tool that is successful will have mathematical feasibility and then real life feasibility, not the framework. So mathematical because real. So that's basically the success story. Now, how do you know that mine is better than yours? After the success is done, my result that you get, for example, 50% loss reduction or whatever you get, that should be the best loss reduction that I get compared to all the other framework that you have. If you can claim, that means my tool is the best. Now, that bestness or the criteria of best is dependent upon state of the art, which means what others have done. So if the maximum loss reduction is 49, I get 51, that means mine is the best. How do you know that that's going to be the best in your life? That you have to prove through, for example, global optimal point like optimization gap, and there are some criteria for doing that. So that's basically the tool with the model. Now, parametric optimization tool. Many people claim that this is good in the soft computing world. And unfortunately, there is no model associated with that. So how do you make the parametric optimization tool exactly like this framework and the model-based tool, and then say that it's better than the model-based tool? First step for that is this parameter space that you are developing or parameters that you are generating should come from a model. And that model that you have, whether it is black box, gray box, or mathematical model, real green model, doesn't matter. That should be defining a scope for this parametric optimization that is feasible, real life. That's number one. Number two, the parameters that is generated in the parametric optimization would cover all the nonlinear points of the real system. So the parameters can be generated properly. So I don't know whether I answered your question.
Basically, sir, actually, nowadays, 10 number of it's really available. Okay, one can download, one can see, but whether you are getting the good result or desired result, that is different thing.
Very different thing.
That will come after analysis.
That's one matter.
What's going on inside, nobody knows. That is the problem.
So the tool and the solver, what is going on inside, you don't have any control as far as a electrical engineer is concerned, especially, software engineer may be talking differently. But what you are giving in and what you are getting out, you have a control. You can understand. That is where the key importance of modeling. So in this kind of framework, you are actually developing models that are concrete. That is a fallback of the parametric optimization. I'm not against soft computing, by the way. I'm just saying in general. That's a problem of the parametric optimization, because the parametric optimization don't have that framework, right? That model is giving. But if you can develop a good model for that, that also should work pretty well. So the focus that we have to work on, I believe, is not to use tools and solvers blindly, but develop good models so that tools and solvers can be used to solve. And that should be our strength, not because I don't think I can understand fully what a Gurobi solver is doing mathematically. Okay, so I'll stop right here. Any other comments, questions?
At least apply process for understanding from the basic how this is applied for books and all this is.
So the toolbox and solvers doesn't do anything with power grid. That is solving a bunch of mathematical equations. So you don't understand anything. This toolbox you are applying to power system through your model. So nobody can apply the toolbox or a solver to the power system without a model. So I am developing the model and I am applying the toolbox. So how these toolbox are used and how this toolbox is applicable, or how the solver is applicable for a power system problem, is an exploration done by you as a power engineer.
When we read the transaction paper, people to understand those things, how they are running, how they are applied. So from the basics, there are any examples or any tutorials.
So nobody is applying in the transaction papers or any work that is done by researchers or anybody. Nobody is applying the tools and solvers. They are not applying tools and solvers. What they are using is they are developing models of electric grid. And models of electric grid development is fundamental. What is fundamental to that? Like what we are discussing, power flow, optimal power. That model development is electric grid model. So if you are using a power flow model, that power flow model remains the same. It has got the same fundamental equation. You will be able to see in any paper the same fundamental equation. But what is the difference? Difference is how do you same equation, how do you put it in, I call it casting. Remember I called it recasting. How do you represent that same equation in a framework that can be understood by the tool and the solver, and using the tool and the solver to solve it. That's all people are doing in any research paper, anywhere you go. Now, why they prefer some tool and solver? There is some advantage that they claim. That advantage, whatever they claim, they will claim in the paper. But that is not the advantage of the tool and solver. That is the advantage of the model that they are developing to tool and solver. So if you look at, if you read all the paper, every paper will have similar kind of equations, voltage equation, power equation. But it is recasted in a different way, meaning same equations, like for example, I square R. I square, you call it L. And when you say L, it's LR. If it is LR, then you can solve it using linear programming. And solve with this L. And then once how to get I out of the L, they will discuss they'll use some mathematics methods to get I out of L. But at the end of the day, it's still I square R. So whenever you read a paper, stay on the modeling side and understand the modeling. And that's what I was trying to explain to Sorry. That if the models are not developed just by parametric, somebody says that, oh, I got a bunch of parameters, and then in particle swarm optimization I got this number, and this number is very good, best. There is no you cannot believe. You say that, well, that is useless, I don't know what to do. But if they say these parameters are based on the power flow, I develop these parameters based on, so then who is doing that? We do. That's what they are publishing, not the tools and so on.
There are some standard already developed. Then we are telling that we have modified some of the parameters and introduced some of the parameters, and we have got this answer. This is the correct way of telling it.
It's context specific, so I cannot answer whether it's correct or not, but if you can give an example, then probably I can answer. So are you saying that you get a parametric set from the real system?
That I can order what we do. That I see that in correct equation A, those values what we get, constant value that I get. So whatever we get is different for different flows. And when we simulate it, so if we are trying to bring some more parameter and we say that this makes more accurate, something like that. I was trying to do that. I was asking about chip model and chip model.
Zip model, what?
For particular node, there will be a particular value not going from ABC, right?
So you are collecting the data from, for example, output from the light bulb, something. You get voltage, current, power, or whatever. You get this bunch of this number. Then you come up with a number for the values for a zip one, and that value that you represent exactly the characteristics of the light bulb. You can actually, and you prove that with the characteristics of the light bulb performance for different conditions. And for each of those conditions, the characteristic of the light bulb can be characterized with the help of this equation with the same value of A, B, and C, which is tuned by some engine. How are you doing it? Because you are proving that with the data set that you are developing, whatever model that you are doing. That modeling that you are developing, the data that you are generating, whatever you are doing, is the contribution. You are not the tool or the particle sum optimization, whatever it does, right? But that tool is valid for that's parametric optimization. That is actually what I was talking about. But that same tool, suppose you use it to find out loss minimization function of an electric grid without having to go through voltage constraints or power constraints on the electric grid, the tool invariably will fail. You can get a loss, but that is not going to be feasible. So, which you will say that, oh, your paper is, you publish something, but it's of no use because these are the things is not covered. These are the things. So, what is the problem? What needs to be covered? What are the things, details that you need to study there? If you understand correctly and you're solving the problem, yes, that has got a value. That is the paper, not the tool or a solver, right? Because you're borrowing the tool. If you can consider the condition for the tool and solver and say that, well, this tool is useless, that also you need to consider. So, for example, if you have a nonlinear equation, power equation, and you run it through an linear programming, then you are using the wrong box to do the right thing. So, you don't have the knowledge that you are using it. So, people will say, hey, your method is completely wrong. So, that's again nothing to do with the tool and the solver. It is to do with you are not able to model it properly. So, any paper when you take it, we don't really consider. There are some things which you cannot even understand, then you do it not properly. For example, solver that you are using. In feasibility nature of the solver, you don't know. And you put an equation that will make the solver go to the infeasibility nature. And you solve it without knowing. And then you get a result. When you publish it, the person who is actually working on the solver or who are actually knowing about it, he will say that this is not good. What you do, you take that comment and you say, I got a knowledge from him. I will improve myself. And you don't publish, that's okay. Because you know you're getting learning out of that. So there are people who actually does that for a living, right? So yeah, I think you understood the one. So you should be focusing on those need, what I am, my contribution, and how that helps solve something. That's so we have some time, I guess, right? Half hour or something. Okay, 5:15. You are saying that, well, will we be stopping here? That is something that I want, right? Okay. How many of you are tired? Nobody wants to say that I am tired. If I say I am tired, then you will lose the attendance, right? I mean, whatever is, what's 90% or something, so. Okay, I'll do a trick here. The trick is, there is one topic that we need to cover today based on we are giving you full meal, okay? So sometimes it's overflowing, but we are not going to say that you have, whatever we are offering is different from what we have, what is that called, visualized or before. So there is one topic that we need to cover today is modeling of power grid for power flow and time series power flow with DERs. So this is something which needs to be discussed today. So what I'm going to talk, since we have only 30 minutes, what I'm going to talk is I'm going to give you like the same thing what we talked about. What is the problem? What is the need for the problem? And how we can solve the problem with the model that we can develop. So just key aspect. So from here you will see modeling of a power grid for power flow. Do you know it? Yes or no? Did you model the power grid for power flow? Did you run the power flow? Did you model the power grid for power? Or you did not run the power flow? What did you run in the morning? What did you do? Example right now. Forward, backward sweep. What is that? It's a power flow. Yeah. No, I didn't know anything. It will be like more like at the end of the day, you'll say, what did I do? I don't know anything. You did run the power flow, yes? Did you run the power flow for a transmission network? Newton-Raphson power flow equations? Yes, we did. Either you forgot or you're very tired. I would think that it's the second part. It's, maybe you are getting to the end of the day. So we did model the power flow for transmission network and distribution network, right? We did that. I mean, we did do the power flow. We did model the electric grid also. Remember when we did model, we modeled the generators, we modeled the transformers, we modeled the transmission lines. We said the model of the distribution network to 3 lines. Remember the difference? OLTC. So this is not new. Why am I saying that this part there? I'm giving you a specific things what is these two. How about modeling of distributed energy resources? Did we model a PV farm with the inverter, 1.2% capacity inverter, reactive power, active power? We did model, on that. So have you done time series power flow? So we did not do time series power flow. So what I'm going to talk in the next 30 minutes, how do you convert, what is time series power flow? How do you convert a power flow to a time series power flow? Why do we need a time series power flow? Where will we use a time series power flow? Okay, you should be able to connect the storyboard. So this is the only thing that is not covered, is missing. And I'm going to focus on DER. Where are DERs located in an electric grid? Transmission system, distribution system, more located. Distributed energy resource. Where are they located more? On a distribution network. Okay. Since the DERs are located on a distribution network, we are going to focus on the power flow for a distribution network. Okay. Do we know what are the characteristics of the distribution network? Lines. There are two important characteristics of a distribution line. One characteristic, distribution lines are not transposed. Since they are not transposed, what happens? It creates unbalanced nature of the distribution network. Because of that, you have to model the distribution lines in three phase, not on one phase. So we model the distribution line in three phase, and we got a 3x3 matrix. Remember or not? We just did it. We got the number. So that is one. Second, distribution lines are going to be multi-phase lateral, means one 3-phase, 2-phase. Distribution lines has voltage regulators. Distribution voltage regulator, step voltage regulator. Distribution lines are zip load. Distribution lines has different transformer connections types, Y connection, delta connection. Distribution lines has shunt capacitors. Distribution lines has multi-phase DR with constant power factor capability and voltage control capability. So, if you have an inverter, that same power from the PV coming from the inverter can be used to deliver the active power and the reactive power, not worry about the voltage. Okay, such inverters are considerably called non-smart or not smart inverters, which is delivering P and Q. So what from the PV farm ask 10 megawatt, will PV farm ask 30 megawatt, you deliver that. So, such the inverters are model generally called PQ type. Okay, it's like a load. Okay, such inverter or the PV plus load is called net load. Only the difference is that it is a negative load. You agree? Okay, so it's called PQ type. The other type of inverter is basically controlling the voltage at the point by supplying reactive power. And such inverters called QV type. Much like your reactive power that is coming from the. Okay. So I'm going to talk about a method which is not discussed. Unlike forward backward sweep, I'm going to discuss about a method that can be used to solve power distribution system power flow. Okay, and that method is called current sensitivity method. Okay, so in this current sensitivity method, the good news is that you can develop in the distribution system, the best matrix can be divided to develop the Jacobian like this. So this is G11, B1, G12, B2, G21, 2 by 2 matrix. We can develop the Jacobian like that. And the current sensitivity matrix calculates the current error from the power. So if you may recall, we did this just now. Do you remember? What did we do? S load divided by V. Remember that we did? So this is a forward backward sweep and V square divided by C. The only difference is that instead of adding the drop I times Z, remember that we added the drop I times Z and calculated. We don't add a drop with I, we add the drop V square divided by Z. So if you do that, you will get a current. And you can calculate all the currents in here. From that currents and from the sensitivity matrix, you can calculate change in the voltage. In the forward backward sweep, we calculate the change in the voltage by the IR drop. Remember? And instead, you are not using that, you are doing a different way. That's the same thing. This is what I call it as same top we are looking at, but you are looking from a different same equations, right? There is no change in that equation. So this is how you run a power flow model for that specific setup. I'm not going to talk about that in detail. So you can compare the power flow for different setup and then so forth. Let me talk about the time series power flow. Okay. So if you look at a power flow, this is important. We're just looking at this. Look at a power flow. You run the power flow. What happens if you have a change in the load in an electric grid? What do you do? How do you run a power flow? In a power flow, will you change the loads? When you run a power flow one time, it's a constant. What happens? Is the load constant all the time? Load is changing. What happens if the load is changing? What do you do with the power flow? You run power flow multiple times. Okay. So these are snapshot. We call it take a one power run, take a next power run. So done at snapshots. How many times you do it? Well, depending upon whatever way you do. You wanted to get a peak load, on a light load and medium load, 3 times is good. You run it. With the high penetration of DERs, what is happening is this number has to be increased because the net load, if it is DER plus load is changing, DER is also changing. Correct? So you increase the number. So what you do is, ideally, you have to do 8,760 times in a year, which means one time in 1 hour. That's what people say. That such power flow is called, such study is called 8760 study. You can Google and search and you will see 8760 study, which means every year the PV is changing, the load is changing. You kind of mix and match and run for every time. So, quasi-static time series simulation is a sequence of steady-state power flow conducted at a time step between 1 second to 1 hour. Okay, 1 second to 1 hour. So the first step is take the power flow, run many times, 1 second to 1 hour. Okay, that is not considered as time series power flow or quasi-steady-state power flow. During a QSTS, the discrete control device like tap changers, voltage regulators, switches and relays can change their state from one step to the other. Right? You have a regulator and one person, it can change the step to the other. In the time series simulation, you will include that changes. Okay? Then, so I told you the step. Power flow, multiple power flow done in a year, time series power flow, which includes the changes of the devices, discrete devices on the power. For example, voltage changes in the voltage regulator. So, no numerical integration, differential equation. Okay, it is just the changes on the discrete time step. Using an accurate load and generation time series data, QSTS, quasi-steady time series simulation can be used to quantify the magnitude and duration of DR impact. Now you understand the difference between time series power flow and the normal power flow? Yes? Okay. So, I'm going to give you an example. Okay. In this example, what we are doing is, we are including a device that changes in steps at different time. Okay. Can you name a controller that changes when the time changes? A controller that changes the voltage, or a legacy device that changes the voltage. There is a device in the electric grid, we talked about it. It's called voltage regulator or load tap changer. It changes the voltage when the time changes. Remember that? We talked about it. Yes. So what happens if you do multiple power flow without taking a regulator? At one point, power flow is done. Next point, power flow is done, taking care of the voltage. But the regulator is changing the voltage. Do you need to consider that or not? Ideally, yes. Otherwise, your power flow solution is not correct. Okay. If you consider, then the power flow will become quasi-steady state power flow. We are considering operation of the legacy device. So, I cannot go in detail about it, but because maybe time, but this is a representation of a control of a transformer, tapped transformer. I should, I think, explain a little bit in here. So this is a transformer high, transformer low, a variable transformer, and line is connected, and this transformer is tapping the current through PTs and CTs. Everybody know PTs and CTs, potential transformers and current transformers. So it's tracking the power through PTs and CTs, and that power is going to go through voltage relay loop, and it is trying to look at the voltage, and that voltage is here to change the tap. This is an operation of the load tap changer. Okay, so we talked about the load tap changer. What is a load tap changer? How it works? It looks at the load and then tap the transformer voltage. Okay, so now you have a question. I think we discussed this. We look at the load, meaning you're looking at the drop in that node and then tap it. Okay, so this drop is generally called line drop compensator. Okay, so what is a line drop compensator? It looks at the line of the electric distribution network and look at the point where the voltage needs to be controlled. So I think I draw a voltage drop equation from the substation to the last point, right? If I want to control that last point, I cannot take the voltage at this next to the transformer. I have to take the voltage or the drop somewhere else, the current on the load. So normally what you do is that this line drop compensation will look at a point on the distribution network somewhere 2/3 from the substation. 2/3, 1/3 is a thing. So you go to 2/3 point and then take that load connection from there, or load drop from there. So that is represented in the regulated point, and then CT measures that, calculate in the form of a drop, and then regulate the voltage. Okay, so it's a compensator, impedance settings, voltage level settings, bandwidth settings, and time delay setting. These are the 4 things that happens on the regulator. So what we do is we do a model of this whole thing in the power flow, and you include that model of that transformer along with the power flow. Okay, so what we did now, we did the power flow model convert into time series power flow model. Okay, and these are some of the results. This is the result from the real model and the field device. So where it is used, if you look at a time varying load profile for a load, and you look at the initial tap for the LTC and the final tap for the LTC that is changing, the voltage profile each phase of the node 8 of the 123 bus, you can see this is with no regulator, this is with regulator. So the voltage with no regulator and voltage with regulator, you can actually see how much voltage changes. This is not a this is not a new control that is doing the control of the regulator. This is just studying what is happening in the electric field. The regulator is moving, it is also getting the information what the regulator is doing. We need that, otherwise the power flow is not complete. So that's what it's trying to do. We can see that power flow in here, the voltage in here, which is with the regulator. This is one application. What's the second application? Let's assume you have a PV farm changing. The LTC is tapping. You want to look at what is the voltage with the LTC tap. You can look at the voltage profile with the LTC tap. Okay, are you following? Yes or no? Transformer is tapping. You are getting the model considering the tap of the transformer. And then you can use to see how much the DER voltage changes and how that can be studied. So I'll stop right there. Probably that's it. I think people started looking at the face, punching out a little bit. So having said that, I hope you got a glimpse. Quasi steady state time series power flow means along with the power flow, including devices that is changing in a step change between times. Okay. So you model the device, include that in the quasi steady state power flow, which represent the real system when the input changes. Any device can take. Any time dependent device that is changing. So in battery operation is basically, battery is considered as a time dependent constraint. So it actually changes with respect to the operation. Include that. DR, you can include that. You can model any time dependent device, not the very fast changing, because that needs probably integration or differential equations, or but it's like minute range or that kind of changes that happens. You can. So such models, development of such models are required. It is even required now because it's PV changes in it. It gives you a realistic path. So there is one I couldn't, I forgot about it, but I will put that. There is one article that we published on this in a transaction or some journal. You can read that. And I'm not saying that we published great, but that's one example. There are several people, doing things like that. But the idea is, when you model it, you have to be realistic, and then you have to include that part there. And one example that we showed is a transformer tap. Basically, that's a must include. Or now, if you have a PV from reactive power contributing to change in the voltage, you can include that. Slow, not fast. So you don't have to do a cumbersome, differential equation or optimization algorithm. Nothing. You can just do this for a small algorithm and then try to see what happens in the real field. Probably have enough for today. So tomorrow when we come back, we will start now moving from moving from steady state condition to dynamics a little bit. So the dynamics will be, and the time dependency and all that will be the next 2-3 days. Our goal will be 2 days rather. Last day I think probably will cover newer topic or advanced topic or something, but that's our goal for tomorrow. I hope you are following the time dependent nature, and keep us posted if you have any questions or any comments. You want some area that needs to be, I think on Friday talk we can also do look at some specific questions if you may have on some areas that you think we should cover.
Sir, there will be examination on Friday.
There is an examination also on Friday, so keep that in mind. If you don't do well on examination, that will be bad. So you have to do well on the examination. That's another thing. I am not going to give you I think we should give you that problem, right, for the homework assignment.
Sir, assignment you can give because this is one of the parts of this course. So one assignment, sir, you can give them.
So what I will do is
that can be accessible, like that we can assess. And
correct. So what I am thinking is that I will give you these few slides that we have done for the forward backward sweep problem.
Assignment is mandatory actually, so you all will try from your side to complete it, and then again we will meet tomorrow for that.
Do you want the problem again, or you got all the numbers you want to solve? Do you want me to formally give a question with all the numbers again to you? forward, backward shift, or you already got the number. You just will solve it. Same number. You know what a number means, like impedance. And how many of you think that I should give that problem again? 3. Raise your hand. 1, 2, 3.
Here also.
2, 4, 6, 8, 10, 12, 14, 15. 15 failed. It's more than 15 here. More than 13 here. You need a 50% mark majority.
Is it clear regarding the assignment? What assignment sir has given? Any confusion?
Okay, then why do you need? I'll send it. No, that's it. Yeah. So that's it. So I'll send you the assignment to you. You can broadcast, right? I'll give it to you. And then it'll take 1 hour. I'll put this back into the Word file and then I'll put it here. And maybe 1 hour. I have to prepare. I have not. It's in the slide.
Okay. Okay.
And then you can send it out.
Okay.
Okay. Thank you all.
Thank you, sir, for this nice session, because you have focused on so many things regarding the optimization, and I think you all have benefited with that. Again, we will meet tomorrow with the new lecture topic, and we'll proceed with that. So, meantime, you will just do the assignment from your side, all right? And then, if you will have any confusion, you can clear in tomorrow's tutorial, or sorry, in lecture class itself. Thank you. Thank you very much. PPT, I think it is not possible for right now. PPT, it will be, yeah, we have to compile at the last. Yeah.
Specifically looking for some like share. In general, you are looking for or for